morning. Welcome to the second day of the workshop. Hopefully you've had a good first day, and I see all of you have made it to ESRIN for 10, which is great. Welcome to the session on adapting foundation models to geospatial data. We'll have a lot of really interesting presentations on foundation models for geospatial context. Maybe just for us to introduce ourselves, my name is Anna Jungblut. I'm a research fellow at the ESA Climate Office.
Good morning, everyone. Hamid Al-Mahmad. I'm a faculty in Clark University.
And without further ado, we'll get started with the first speaker. So the first presentation will be on denoising diffusion models for augmentation of optical satellite data by Schulte-Strathaus.
Wait, can I use the notes in my laptop? Okay. Sorry.
And just as a reminder for all speakers, so you have 15 minutes with maybe about 12 minutes for the presentation and a couple of minutes for questions.
If possible, yeah. Does that work?
Just let it slide down there. Yeah.
The question is how I move away.
Oh.
One sec.
Maybe put it on this and then you have to hold it, I think, otherwise it will slide. Put it here, but keep it there.
Fine?
Yeah, but make sure you keep it, otherwise it may slide.
I think it's fine.
Yeah?
But
Okay.
yeah,
And
I'll
then
be
you
fine.
click this one.
Yeah, thank you.
I will show you like this at 12.
One sec. Hi. Right, I hope this is working now. Hi, I'm Tabea. I'm presenting a paper I wrote. So I'm LMU now, but I used to be University of Glasgow, and I did this work while I did my year abroad at the University of Glasgow with some people there. And I do also want to say that I'm sponsored by ESA Academy to attend, so very grateful for that. Yes. Right, let's start. So in our work, we used, okay, actually, let me remove my headphones. We use denoising diffusion models to do two tasks. So in general, as you know, all generative models just learn a joint probability distribution to generate new data. And there have been a lot of papers that show promising applications for satellite imagery. And we explored their use to create and augment multispectral satellite data sets. And we achieved two independent goals. First of all, we are able to create realistic artificial RGB datasets containing user-defined features. And this is like the first half, so creating artificial RGB data. And it's very important to make that distinction because I think sometimes when I talk about this, people will tend to get it mixed up. And the second part that is only via the model related to that is we augment RGB data by predicting the NIR band accurately on ground. So imagine you have a satellite that only captures RGB data, and then later on ground, you predict the NIR band. Yes. And as of now, we're looking into extending, we're using Sentinel-2 data, and as of now, we're using, we're researching if we can extend our model to historic data in painting tasks and non-Earth imagery, but I'll talk about that in a sec. Right. So in satellite remote sensing, there's like three ways of perceiving an object: reflection, emission, and a combination of both, as you know. And classical... Oh, no! No, I'm sorry, I forgot about that. OK, but it's not working. Why is it not working? No? What is this? Technical support? Yeah. OK, so this is the second slide. This was the first slide. But OK. Yes. So classical, like very old classical satellite imagery, is usually the natural image, so three distinct bands, red, green, and blue. And if we combine these bands, we yield a natural color image, as you'll know. And then if you For instance, a natural color from Sentinel-2 will be wavelengths, I think, 490, 560, and 675 nanometers. But also, obviously, you can record data outside that spectrum and combine it to get combinations such as the vegetation index, NDVI, or color infrared. And a hypothesis of this paper is that it should be possible for a diffusion model to predict near-infrared data from information gained from analyzing the relationship between said band and RGB data. And a simple pixel-wise transfer seems unreasonable, as different materials often have the same color while varying a great deal in their near-infrared ranges. So we assume that our machine learning model is able to recognize a relationship between structures in the RGB image and the NIR band, thereby enabling simulation of the latter simply by introducing spectral features to different surfaces of the Earth. And actually, there's another different point. Research shows an interesting relationship between the blue and the NIR reflectance bands over the day, because their composed vector follows a nonlinear closed-loop curve as the Earth rotates, which, to me at least, suggests not only additional frequency-based information for the model to draw from, but also that it could infer knowledge about recording time. Right. So while obviously it could be very interesting to look into the simulation of other spectral bands, we focus on NIR bands, as it is the band that is, I guess, most broadly used in Earth observation tasks. And combining the NIR band with visible spectral data yields important indices. I talked about that, normalized vegetation index, the normalized difference moisture index, or representations such as false color, which is what you will see in the presentation, false color. And there's a question that I've also been asked quite a lot. Will the Earth's natural emittant influence what the diffusion model works on, what it perceives? No. Because most of the Earth's surface materials, such as water, stone, or vegetation, they emit in the long-wave infrared region, so 8 to 14 micrometers. And even when heated up, for instance, by a forest fire, their emitted radiation shifts not further than medium-wave infrared, whereas we work on near-infrared. So there shouldn't be an interference there. And it shouldn't be corrupted by thermal emissions of the observed bodies, which does actually make NIR bands a sensible choice for simulation. Right, okay, so diffusion models, as you'll know, are... No! Oh, I'm so sorry. Yeah, I shouldn't forget about that. Okay, also my first presentation, by the way. So diffusion model... Okay, so diffusion models, as you know, are a type of self-supervised generative model, and they are inspired by non-equilibrium thermodynamics. They define, but I'll talk about that in a sec, a Markov chain of diffusion steps by slowly adding noise to data and then learning to reverse that process. And diffusion models have a lot of advantages. The latent variable they use has a high dimensionality, and they are analytically tractable and flexible, which is quite often quite hard to achieve in generative models. Yeah. So how the forward process works is that at each time step t, we add a small amount of Gaussian noise to a previous state, x t-1, to get x1. And R beta in the equation is a very small positive scalar, the variance of the added noise, and we use it to scale down x. And this process produces a Markov chain where each step only depends on the previous one. And for the entire process, as you'll see, we can just take the product of the conditional Gaussians. And instead of computing the noise step by step, what we do is we can sample xt directly from the original data by using this marginal distribution. And obviously, as you can see there, A bar controls just how much signal remains. This, funnily enough, is actually inspired by Langevin dynamics, which is it's the mathematical equivalent to solving a reverse time SDE, but with the Boltzmann constant. Yes, so how does the reverse diffusion process work? In the reverse process, we aim to, well, reverse the noise we added during the forward process, and there are some important parts to this. So we model the reverse distribution starting from pure noise and sampling, I did remember, later, and sampling each previous step condition on x, where p is the learnable Gaussian distribution with the mean and the covariance or uncertainty predicted by the module. And we can predict the noise by using something that's called a reprogrammation trick, but I think that's kind of what you do in all models. Yeah, so we use a simplified loss function of the mean squared error, and we use a cosine schedule for our variance, which is just due to the nonlinear data that we quite often encounter with sinusoidal data. And obviously, the backbone of our model is just the unit, as always. I don't think I have to talk about that for that long. Very, very classic unit. So, sampling. And bear in mind, I'm not talking about image generation, not the NIR band prediction. So in our sampling process, we generate images by iteratively denoising random noise. And we start with a latent variable from the Gaussian distribution, as I mentioned earlier, and the model progressively refines it by reversing the diffusion process. And at each step, the model predicts and removes noise, moves the sample closer to the target data distribution, and a cosine schedule that controls variance for stability and precision. Yes, we are able by that to produce detailed and quite realistic images while preserving the diversity of the image, as you'll see in a bit. And for our evaluation, we use the Fréchet inception distance, which just compares the data set, the generated images, to the real images. And here are some examples. We trained on different biomes, or, well, different categories, on the Eurosat data set. Sorry, thank you. So this would be river. And I think this is actually one of the nicest samples we got because you can see quite fine structures in the generated river data. You can see the river beds. There's very little logical errors, as in bridges that don't end or rivers that just, well, stop. Oops. It's just, well, it's just a magnified example but of some of the images you just saw. Here is forest, which unfortunately you can't see that finely on that, but the structures are actually quite nicely preserved in forest as well. This would be annual crop. And as with river, we have very, very little topological disturbances, which is quite nice, so no heterogeneation there. This would be an instance of residential. It's a bit more difficult to get the fine structures there, but I think the model got it quite nicely. Yes, and that's just zoomed in. So for the NIR band prediction part, the proposed model, or well, not proposed, the model operates on a multispectral data set, so RGB, and near-infrared channels. But during training, only the NIR channel is corrupted with Gaussian noise, while the RGB channels remain fixed. And the model's task is then to denoise the NIR channel using the RGB channels as static inputs during both training and interference. And this removes the need to predict the visible spectrum and focuses solely on restoring the NIR data. And this model, again, follows quite a normal UNet architecture with, I think, 85 million parameters, something like that. And it takes the 4-channel input, clean RGB channels, and the noised NIR channel, along with the positionally encoded time step. And the unit then outputs a single channel prediction, right, representing the noise added to the NIR channel. Yeah, and this model, we trained it on 64 by 64 Eurosat images. And there's an interesting part to it, because we found that just by using the unit, we were not able to get good results. So additionally, we came up with a little trick. In addition to the direct RGB input, the model is conditioned on features extracted from the RGB channels via an additional encoder. I'm not going to talk about that further because there's a paper. Basically, the encoder is just the first half of a unit, and it generates immediate feature maps from the RGB bands. And these are then concatenated with the primary UNet's features during the downsampling stages, which allows the model to exploit spatial and spectral correlations from the RGB channels to improve NIR reconstruction. And, oh yeah, we use the structural similarity index and the mean structural similarity index to evaluate our results. Yes, I'll show you my results in a bit, but they are in false, yeah, these are my results, thank you. They're in false color. And I will explain this because this is the slide that people always get wrong. On the left-hand side, you have the ground truth RGB. So this is what the model gets right? The second image is the ground truth NIR band, so the model has not seen that. And then on the right-hand side, you can see our simulated NIR band. Well, it's not the NIR band, it's the NIR band in false color, but you can see it much nicer, the differences when you use false color. So I do actually think we get quite nice results. They do look very similar. There's obviously some little disturbances there. Another example of river, and you can see it's a bit like grindy within the simulated river, but still quite good results. And then I was very surprised to see how well it recognizes structures in the forest. So yeah, this is annual crop, and this is residential, which I'm actually quite proud of because it looks very nice. Yes. So what are use cases of this? I would like to know that because this is not my specialty. Obviously, artificial satellite image generation, it offers significant benefits to like environmental health monitoring, urban development, disaster management, and we can use these synthetic images to augment training data sets for machine learning models, overcoming challenges like the scarcity or the cost of real-world label data. And by simulating diverse environmental conditions and rare phenomena, such as forest fires, they improve the model robustness and generalizability, and we can support researchers in making their models more interpretable, for instance. And additionally, our model can be used to bridge temporal gaps in data and mitigate, for instance, cloud cover issues. Scotland comes to mind. Enabling more continuous and comprehensive analysis of terrestrial phenomena via a slightly unbiased data set. Obviously, you can introduce biases though. And it could further be used, that's actually what we're trying to do now, to adapt data sets to specific events, such as fisheries or boats. Yes, and last slide. So for NIR prediction, obviously, this is actually how, thank you. This is how we came up with it, because obviously quite often CubeSats and small satellite missions, they suffer from having very limited space for installation and for cameras. So quite often they find it difficult to get uncompromised NIR data. We can obviously mitigate that issue and the corruption of pixels by generating the image, the band later on ground. Yes. But I think there is a lot of different use cases, and I'd be very interested in knowing if anybody comes up with some more. So what we're doing now, again, is we're using it on historical data, which is quite nice, because we're trying to replicate the NIR bands of very early Landsat satellites just by adapting our data set, and it does actually work quite nicely. I was very surprised by that. We're trying out in-painting tasks, so again, adding fisheries and boats to our images, and supplying additional data via an MLP, which, however, is not that easy for the model to understand because it's a non-linear task. Trying different combinations of bands, and we're actually working on using it on the moon, which is quite, weirdly enough, it does work, but there's still a lot to do. Yes, so I think that's me. Thank you.
Please find the speaker in the coffee break if you have questions. We'll move on to the next speaker now, which is a presentation on multimodal, multitemporal, multispectral mass autoencoders by Antoine Labattier. All right, I'm guessing they're not here. So I know for a fact that the third speaker is here. So why don't we move on to the next presentation and then see if Antoine shows up. So I invite Jasmine Lambert up to talk about addressing cloud and shadow-induced data gaps in complex terrains for forest monitoring.
That's a surprise, so now I'm starting earlier than expected. Glad that I have the presentation ready. Let's check. So, well, maybe just a few words about the Austrian Institute of Technology, which is my employer, and here of my two colleagues. AIT is the Austrian Institute for Technology, based mainly in Vienna, with about 1,500 employers. And this took me as a surprise when I first came to Austria and Vienna. And they are basically doing research at the interface between basic research and applied research, a bit like the German Fraunhofer concept. But now let's move on. So what is the current situation that we have? From what we've seen so far, massive amount of Earth observation and geodata altogether is available. So we are clearly in a big data regime here. Well, and this caused a second development, namely the onset of foundation models, pre-trained foundation models that offer a real interesting opportunity for scientists to work with. But of course, well, we need fine-tuning for going down to domain-specific tasks and to capture the challenges there at hand. So making it more concrete, we have on the left side raw satellite data, for example. And if you consider a country like Austria, there are a lot of mountains as well involved, and this causes clouds, shadows, and, well, other things that basically disturb from the tasks that we are in the end working with. So how do we get from the left side, from the raw satellite data, to actionable insights? And in our specific case here, we are working currently in the domain of forestry, although being more, well, people from the data science and machine learning domain with various backgrounds. But how will we come to wind throw detection or anomaly detection in forests? That's the big question here. And our project, SAFIR, it's a national project. Although national, I mean, we have already associated partners at an international level, what we are aiming to do. So what we are trying to do is removing things like clouds and shadow to improve the images and receive higher quality of data. And the other thing that in particular my colleagues from the Vision and Automation Group pursue is using UAVs to get actual ground truths in the forest, of course, together with forest managers. And in the end, we would like to make prediction from high quality data with respect to the specific tasks at hand. So let me briefly introduce you to the consortium. SAFIR stands for Sentinel Assisted Forestry Insight and Research. So AI for Climate Responsive Forest Monitoring in Mountainous Regions. And it's a, well, medium-sized national project in the Digital Twin Austria call, which was launched first last year, with a project duration of 3 years. And we just started, what I think, half a year ago, yeah. So coordinated by my colleague, Philippe Fantayende. And what I'm particularly grateful for is we have the important stakeholders on board, namely what you can see in the lower, does it have a, nah, it doesn't, a pointer? Well, but I can guide you still like this. So we have important stakeholders already on board, which is the federal Austrian forestry providers, as well as the Forest Research Center, the BFW in Austria, both dealing with forestry data and really, well, working in the forests. So, and as additional project partners, we have the EODC, the Earth Observation Data Center, which is like a data hub European-wide for satellite EO data. as well as a Portuguese partner, INESC, which is of really high importance because we would like to have geographical diversity for the data we are collecting. And we already have associated partners from, well, a few other countries like France, the LSCE, or Germany, Technical University of Braunschweig. So, but what are the key challenges that we need to consider for remote sensing in the forestry domain? Currently, there is, well, a necessity for having a higher frequency of available data because with climate change ongoing and, well, natural hazards like landslides or stuff happening more frequently or severe weather and wind throws, we need to get a quicker, better idea what's happening on the ground in the forests. And in Austria and other countries probably as well, we have this specific situation that we need to take into account the mountainous areas. They are remote, so it's difficult to go there and really check. Well, due to this, you also often have clouds and shadows in your satellite imagery. So this is the idea of our project, that we would like to improve the situation and to give scientists or the forestry managers the data they need at the frequency they need. So here on the right-hand side, you can basically see how it looks. So you have on the Sentinel-2 images as well as GeoLand ortho images, and you can see a typical way how the shadows affect the images here. And, well, I won't give you the full details of what things we all consider, but to give you a better feeling of what we are doing is, well, you need for the one thing, for example, to have topographic corrections. We use digital elevation models in order to better capture how the light intensity changes due to the slope and aspect ratio of the geographical area. And well, I mean, if you know how the physics at hand works, why not use it and correct the data for it immediately? For the deshadowing and declouding of Sentinel-2 images, we had a look at the literature and are using currently, or aiming to use, deep residual neural networks. And basically, we combine here Sentinel-2 and Sentinel-1 data. So it's also a multi-resolution approach that we use. Compare it to the ground truth in order to get a prediction on the right-hand side, to have the cloudless Sentinel-2 images in the end. So how does the idea for our pipeline look like? It's not yet carved into stone. We are using this workshop here to screen what architectures, approaches are around for doing both steps. On the one hand, we use public data that we have been collecting, for example, like my colleague Lorenzo Beltrame, who found LoveDA as a good public data set for starting the pre-training processes. We are, of course, looking into foundation models. And after the first pre-training step, we will use our fine-tuning pipeline for really going from a cloud removal over deshadowing towards task-specific modeling. And, well, our main supervision part is, well, we are considering the task performance loss in order for the supervised model to work. And in the end, it's important to note that we leverage our UAV data for really get there with the task-specific fine-tuning to get really high-quality products. And yeah, how does it look like? We are basically pursuing currently 2 tasks, the wind throw detection. So both tasks were suggested by the stakeholders involved, that on the one hand, wind throw detection is something of really importance, as well as anomaly detections in the satellite bands. That's something that the BFW is currently working on, to put this anomaly into context with some actual physical thing happening on the ground. And we will evaluate our results based on how they perform in these tasks. For the first wind throw detection, we will have a binary raster layer as a product. Yeah, this is how it could look like. I mean, we will hopefully produce first results within this year. And for the anomaly detection, we have time series data, also a raster layer time series data. And well, when at the project end, we intend to put all this into the ESA-GTIF tool, let's say. And now I'm curious, how many of you have heard of GTIF? Still a few. So since this is an Esa-Nasa workshop, I decided to briefly talk about this part as well. So GTIF stands for Green Transition Information Factory. It's something that the ESA has launched. I think it's a rather, in a demonstrator state type of thing. Well, it's a European data and analytics infrastructure concept, and it's trying to go or support the European Green Deal by really showing how you can use Earth observation data with cloud computing and cutting-edge, machine learning AI analytics. And for some reason, I have no clue why, Austria has the first demonstrator ready. So what we will do is we will, at the end of SAFIR, push our data there, our results, and provide them as a layer. And I think with this overview, I will come to the key conclusions or key points of my talk. Well, tackling downstream tasks really effectively requires a lot of domain knowledge and a lot of work. And what we notice that we lack in our project work is a more diverse multimodal data sets in order to fine-tune the foundation models. Otherwise, it's difficult to push forward to specific tasks. And well, my request or hope is that, before we all go towards rushing for new foundation models, it would be important that these efforts are guided by the needs of the Earth observation or geo community. So, thank you.
We have time for one quick question, if there's a question in the audience.
Thank you for this nice overview. One question for your gap-filling process, Sentinel-2, Sentinel-1 based. Can you say anything about the performance in, let's say, areas of complex terrain where you have strong distortions, layover effects, shadow effects in Sentinel-1?
To be honest, we are not really there yet. So our impression that this has an effect, but I think it would be too early to really give exact numbers on how what's the problems they are causing. I'm being honest.
Okay, thanks.
All right, then we'll move move on to the next presentation, which is the second speaker, Antoine Labatier, on multimodal, multitemporal, and multispectral mass autoencoders.
Thank you very much. Hello, everybody. So my name is Antoine Labatier, and today I'm going to present our work on multimodal, multitemporal, and multispectral mass autoencoders for Earth observation. So this work was done at IGN, the French mapping agency, with my colleagues that you can see here. So the context of this work is that IGN, as a French mapping agency, is mapping French territory, and more it's using AI models to do that in an automated fashion. And the diverse application it covers are land cover, land use, agriculture, forestry. And to accomplish its task, it has labeled and published different datasets, which tend to be multimodal, multitemporal, and multispectral. And here you can see 3 examples. So FLAIR is for land cover, PASTIS is for agriculture, and Pure Forest is the latest one for forestry. And there are much more actually to come. So these datasets are located in France, so that's one of their limitations. And they tend to be multimodal, multitemporal, and multispectral to overcome the resolution dilemma, spatial, temporal, and spectral resolution dilemma. So in this context, IGN is wondering, also considering the latest advance in self-supervised learning, IGN is wondering whether self-supervised learning can help as a pre-training strategy to be more efficient, data efficient during fine-tuning on this task. And the second question, if the first question is yes, if there is a potential for SSL, the second question is, should IGN develop its own SSL models, or should it rely on off-the-shelf existing SSL models? So in this study, we try to answer these 2 questions. And so to address these 2 questions, we have some simplification and some complexity that we deal. Here it's more about, on this slide, it's more about the simplification. So as a SSL approach, we adopt a very common approach that you probably know. Many other works here have mentioned it. It's a mask autoencoder. So it's a generative approach where we mask some patches and we try to reconstruct them from the visible patches. We adopt it because it's quite performant and also efficient computationally. And the second simplification is that we only do intra-dataset transfer learning between SSL and fine-tuning. So we do not do any cross-dataset or any cross-domain transfer learning. So we have different datasets, and on each dataset, we either have a SSL workflow where we start with the SSL and we follow it with a fine-tuning stage, or we have a workflow without SSL where we go directly to fine-tuning. And we repeat these 2 workflows on the 3 different datasets that we consider. And the 3 datasets are TreeSat AI for forestry. So it has aerial imagery and then time series for Sentinel-2 and Sentinel-1. So PASTIS is for agriculture crop segmentation, and it has SPOT VHR and Sentinel-2, Sentinel-1 time series. And FLAIR Hub is the new version of FLAIR, which is actually not published yet, but it will be published very soon. And it's for land cover semantic segmentation. And it has aerial, elevation modalities, and it has also time series for Sentinel-2 and Sentinel-1. So that's for the simplifying assumptions. Now we go to the complexities that we actually decide to handle. And these complexities are meant to handle the multimodal, multitemporal, and multispectral character of the datasets. So as you know, the mask autoencoder was originally designed for single images, to process single images. So it's not obvious what we should do when we have more complicated inputs, so multiple modalities, and for some modalities, multiple dates. And so that's why here we have different variants, so different choices of what we can do. And these different choices, they vary in terms of how the fusion, the multimodal and multitemporal fusion is done, so whether it's early fusion or late fusion. So you can see here, if you see the first case, for shared fusion, what happens is that each modality and each date for multi-temporal modalities is processed independently by a vision transformer encoder. And then the feature map in output are fused after the encoder. So that amounts to late multimodal and late multi-temporal fusion. And another characteristic is that the weights are shared between the different modalities in this case. In the second case, monotemp is the same. So we have late multimodal and multi-temporal fusion, but the encoders have specific weights depending on the modality. And then for the last two fusion modes, so for the third one, what happens is that, so we still have a late multimodal fusion, but in this case we have an early multi-temporal fusion. So that means that for any multi-temporal modalities, we concatenate all the tokens from the modality and into a single sequence, and this sequence is processed by the VIT encoder. So there are interactions, cross-attention between the different dates. But we still have late multimodal fusion, and then the last case for the grouped fusion is the same, but instead of considering each modality independently, we also group modalities. So in the grouped modalities, we also concatenate the sequences from the different modalities that are grouped, and these modalities are processed together. So there is early fusion for the modalities that are grouped together, and there is late fusion when the modalities are not grouped together. So that's the complexity to account for multi-temporality and multi-modality. Now, there is also a complexity for multispectrality. So as you may know, the original mask autoencoder, the loss function amounts to penalizes error in the reconstruction. So we try to reconstruct the inputs, and errors are penalized either with L1 norm or L2 norm. So that's the original loss function, and there is a variance that was already specified in the original MAE paper, and also in some work in observation. And in this variance, the target is normalized on each patch. So the mean and standard deviations are statistics which are computed on each patch, considering all the dimensions, the spatial and the channel dimension of the patch. And these statistics are used to normalize the target, and then it's the normalized target that is reconstructed. And the variance that we consider goes a step further. Instead of normalizing over all the spatial and the channel dimensions, instead we group the channels into different groups. So we define different groups of channels, and we normalize each group independently. And as you can see, if we look at a very multispectral modality like Sentinel-2, if you look at 10 bands and you look at the histograms, actually you see that there are groups of channels which are very similar histograms and which are actually quite correlated. So what we do is that we define these groups of very correlated channels, and we normalize the targets independently in each group. So that's the complexity that how we handle multispectrality. Now if we go to the results, so first we evaluate the different choices for the multimodal and multitemporal fusion. And first we can look at multimodality. So here we need to look at the three last bars. So the fusion mode and the fusion group S1 and group all. So with fusion mode, each modality is considered separately. For group S1, we group Sentinel-1 ascending and Sentinel-1 descending. And for group all, we group all the modalities together. So what we see is that it can be beneficial to group some modalities together. So for example, just all the S1 modalities, but it's detrimental to group all the modalities together, probably because they are too dissimilar. So late fusion is preferable when modalities are too dissimilar, and early fusion is preferable when modalities are similar. But in all cases, the impact is not that huge for multimodality. Now, if we look at multitemporality, here the impact is actually huge. So the first two cases, shared and monotemp, actually lag behind a lot compared to the other case. So that means that early multi-temporal fusion is highly beneficial on these datasets. So this might be because of the specificities of these datasets, because so TreeSat and PASTIS, the task is tree species classification and agriculture crop identification. So in that cases, the temporal signature might be very important, which means that the temporal interactions are very important. But what that also means is that on these data sets, using off-the-shelf foundation models might be tricky, because most of the shelf foundation models are pre-trained on single images, so they are only compatible with late fusion. So in that case, we would have a performance deficit, which is quite significant. Now, if we go to the results on multispectrality, so here we test our choices of target normalization. Specifically on Sentinel-2, so we use our scheme to normalize with 3 groups of highly correlated Sentinel-2 bands, and we compare to the scheme where all the channels are grouped together, so the standard normalization from the original paper. And what we see is with our scheme, we also have here a big benefit, so between 1 and 2% benefit. So that means that target normalization is actually very, very important. And we also try to compare to another way of doing this multispectral fusion. So instead of having groups only in the target normalization, we impose the groups as separate tokens. So we also normalize each group independently because they are on separate tokens. But since they are on separate tokens, the encoders actually process much more tokens. So if we have 3 groups, the number of tokens for Sentinel-2 increased by a factor of 3. And what is very remarkable is that actually the performance with this scheme of just target normalization is the same, is very similar to the performance we get by having separate tokens. So that would mean that it's not so much the number of tokens that matter, but more how the normalization is done in the pretext task. And so the interpretation is not clear, but I think the literature doesn't say exactly why patch-wise normalization is important. Okay, I think it's the, okay. Sorry, the literature does not say why patch-wise normalization is important, but an hypothesis is that it balances the difficulty of the pretext task along the patches, so it makes sure that all the patches have similar difficulty. And if we have very multispectral modalities where the histograms are very different, and have little overlap, then normalizing across all the channels might end up to very similar to a constant normalization, which depends only on the histogram and not on the patch. So in that case, we would lose the patch dependence of the normalization. So with all of these insights, we adopted a unified approach that does so early fusion for multitemporality, early fusion for early fusion for multitemporality, early fusion for similar modalities, and late fusion for dissimilar modalities. And for multispectrality, we do the grouping only in the target normalization. And we applied this same unified approach on the 3 datasets, and we compare our workflow with SSL compared to the workflow without SSL. And what we observe is a gain with SSL between 3 to 5 to 6%. So this is quite big. And so as a conclusion, we can answer the 2 questions that we ask. So can SSL improve performance and data efficiency on this multimodal, multitemporal, and multispectral datasets? So the answer is yes. So with our approach, so it's not necessarily the end game. So it's not it can still be improved, surely, but already it gives +3 to +6%. So this is already showing that SSL has a big impact. And even on very large data sets, such as Flare Hub, the gains are significant. So to the second question, can we rely on off-the-shelf foundation models on these data sets? So for the data sets that we consider, where the temporal signature is very important, actually, it's not very optimal to use off-the-shelf foundation models because they are only compatible with late fusion. And this has a performance deficit. And the novelty of this study, we benchmarked different choices of fusion for these data sets, and we adapted the mask autoencoder to it. So it was not the plan at the beginning, but because we have these novel insights, we also plan to have a paper. So we plan to have a conference paper that is in progress and will be released soon. But for now, we don't have any. Yeah. And that's it for me. Thank you very much for your attention, and I'm happy for any questions.
Thank you very much for the talk. Please also find the speaker in the coffee break, and we'll move on to the next presentation.
Thank you. Yeah, we are out of time. I want to remind our speakers, if you can stick to the 12-minute thing, we can have time for questions. So please do that so we can have more engaging session. So our next speaker is Chris Rampersad with the talk, Bridging the Spatiotemporal Gap, High-Frequency Time Series Foundation Models with Venus Satellite Data. Chris?
Good morning, everyone. First off, thank you to the organizers for this wonderful conference. It's a real great opportunity to present our results. So yeah, thanks. This is great. Okay, so I'm going to be presenting about time series focused foundation models. I'm actually presenting on behalf of one of our colleagues who's the lead author, Sung-Woo Lee. I'm Chris Rampersad. I'm the VP of Engineering, and I'll do my best to cover for him. Oh, sorry. All right, and I'll try to keep it to 12 minutes. Okay, so just a bit of background on us. If you don't know Earth Daily, we are a vertically integrated space company. So basically, we're focused on data services, data processing, and data analytics. And we support a wide range of verticals, insurance, agriculture, forestry, and mining. And we have one really exciting thing coming up this year. We're launching our own constellation, and we've been building this for the past 10 years. And designing it. Manufacturing started back in 2021, so it's been a long journey and really excited to talk about that. So I'll dive into that in just a couple of minutes. Okay, and to start, there's this really great quote from Yijun Choi. If you don't know her, she's an AI leader in LLMs, and basically what she says is AI is as good as your data. And she goes on deeper to say it's really about the quality or the novelty or the diversity of your data, and that's really the key to build highly accurate models. And why this is important for us is when we look into Earth observation, there's lots of different sensors from NASA, from the European Space Agency, from CNES, from ECMWF. We have this whole wealth of data that we use to build our foundation models, and all the great work that we've done is thanks to the open data. And at Earth Daily, we also follow similar suit. What we do is we leverage those satellites from ESA and the European Space Agency, and what we do is we continuously cross-calibrate our satellites. We use the same practices you'd see from NASA. Kevin from the AI panel yesterday mentioned pre-launch calibration is really important, and so that's the same thing we do. We use the expertise from NASA, and we actually hire some people who worked on NASA missions to do our pre-launch calibration. So in short, we're basically building a satellite constellation that will image the Earth's entire landmass every day. We have 22 spectral bands. It's a 5-meter resolution satellite. And what for us is key is that we have high quality imagery so that we're consistently imaging at the same time every day for that 10-year design life. And what you'll see is we have bands from Veneer, shortwave infrared, midwave infrared, and longwave thermal infrared. So quite a large range of modalities. And that really ties in well to what Yijun Choi was saying, that when you're building these models, it's really important to have highly diverse data, novel data, and scientific quality. So we're underway in the process of getting CIOS ARD compliance for our satellites. And in terms of the design themselves, there's a 10-year design life, and this 5-meter resolution gives us something quite unique. It's basically an extension of Sentinel-2 and Landsat. And in fact, when we planned our band combinations, we looked at what Sentinel-2 and Landsat had today, but then we also looked where the puck is going in the future. And so we mapped our bands to what you'll get from Landsat Next in many capacities. Landsat Next has 26 bands, we'll have 22. And I apologize for the hockey reference, I'm from Canada, so that goes without saying. But today we don't have Earth daily data because we're launching in June. And so we're using Venus data. And Venus is a satellite from CNES and ISA. It's a really interesting mission that gives you daily coverage and coverage every second day over certain study sites around the world. So if you look at the top left, you'll see those little pinpoints. They're areas like desert, urban areas, ocean, ag areas, forestry. And it also has 1 to 2 day revisit. So it's really interesting for research and development. The resolution is actually quite high too from an open data source. It's 4 to 5 meters, and it has great diversity. It has 12 spectral bands. You can see those are really well aligned with Sentinel-2 as well. So this served as our proxy to build some foundation models with really dense time series. And in terms of our company, we do 2 areas of foundation model research. One is something we call PyVit-Fuse. It's a pyramid vision transformer approach. I'm not going to go into the details of that, but if you're interested, there's a paper up there. But what I'm going to talk about is the model that we're building now. It's hot off the press. It's an agriculture forecasting model. And it's really about using very frequent data to forecast vegetation outputs. It can also be used for change detection. And as we went through this process, what we really wanted to understand is what's the importance of temporal and spatial density in terms of accuracy of the models. Okay, so again, you'll see masked autoencoder approach. We followed a suit there, but we did a few different changes. We relied on a different integration of the time series. So we support variable length time series, so we can take a short input of time or a very long range multi-month, multi-year approach. And we also have support for sparsely sampled satellite data, because as you know, with satellite data, you could have clouds, so you might get an image every day, or maybe every 3 days, or every 5 days. So that sparsity we had to handle within the masked autoencoder. And so what we did was we sampled 400 million samples at these 236 sites, and they were composed of deserts and oceans and agriculture and forestry, but a highly variable set of data. And then we built this model, and it was designed effectively for general use, but it was a pixel sampling model. It wasn't a patch model. So that kept the model smaller, and because of that pixel-based architecture, it makes it better in general for vegetation. We also, with the model, it supports 2 different types of application. You could just use the encoder directly, get your embeddings, start building models off of that, or you could use the encoder-decoder approach, where you would feed in a time series, and then you could forecast out the surface reflectance. So if you want to work in image space, that becomes pretty interesting. And with any early development, so this is just a little video of our early masked encoder. We just want to make sure that it's doing what it should. So here we're just using it for cloud imputation to make sure that we can clean up clouds and forecast the surface reflectance. So it was just an initial quick check. But we want to go a bit deeper than that. So what we did was we designed a real-world use case. And so we looked into harvest date forecasting. And if you think about harvest date forecasting, it's quite a complex problem. You don't really know exactly when the farmers will plant. You don't know the weather. You don't know when the farmers will harvest. So it's extremely complex. And what we did was we trained the foundation model off of 1 million samples in North America for corn only. So it was very specialized to that realm. But we did quite a few diverse data sets within the US. And when we did our training versus our testing, we used different years for our testing. So it was independent in that regards. You can see on the left there is some diagrams of the fields and the different harvest date. And what you'll see is the harvest date varies by 1 to 2 weeks or so. And this is just in a localized area. So you can imagine how complex this gets when you go across the entire United States. Or if you're going to do this across the world, it gets even more complex. But what we found was when we used our model, we could forecast in the 0 to 10 day range within about 3 days median error. So what that means is sometimes you're better, sometimes you're worse. But then where it got really interesting is when we forecast out 50 to 60 days in the future, we found with this model you could get to about 7 days median error again. So if you're anything like me, I didn't really have a good context whether that's a good result or a bad result. So we asked our agriculture specialist, is this good? And they basically said, yeah, that's actually pretty good. So if there's any agriculture specialists out there, we'd love to hear from you and talk more about this. We're going to continue to refine this and make this model better, but that's some pretty promising early results. And then with any foundation model, we want to validate that it's working as expected. So we did some sanity checking. The first characteristic is that you should be able to train a foundation model with a limited label. So we took the same model. Instead of using 1 million samples, we used 10,000 samples. And then we also trained a model from scratch. We compared the two. What you see is that yellow, orangey line. That's the model from scratch. The blue line is the one with the pre-trained foundation model, and it's exactly what you expect. So nothing too surprising, but it was just a little validation for us. The next bit of information is a little more surprising, at least from where I'm standing. We wanted to see the effect of a dense time series versus a less dense. So initially, we were going to do Sentinel versus Venus, but we just found there's a lot of variation between the data. Even the bands are a little bit different clouds. So what we did instead was we took Venus data, which is every day or two, and we just temporarily downsampled it. So we removed every second day from Venus. And we thought that was a pretty good representation of the temporal density of Sentinel-2. And so then we did the exact same thing. We trained that model on the Sentinel-2-like Sentinel-2-like temporal model, and then we kept the original model. And what we found was the first model, we got a 7-day median error when you forecast 50 to 60 days out. And when we did the same thing with the one that's sampled by a factor of 2, we got roughly a 12-day median error. So that big change wasn't expected. We thought it'd be a smaller difference. So that's about a 67% change. And I think it relates to needing the early vegetation curves and building that up over time. You get a better understanding of what's happening with the vegetation. I would guess for other applications and forecasting, you could probably get away with less temporal density, but this one for sure relied on that density. And then the next thing we did was looked at the spatial resolution impact. So again, we're trying to think of Venus versus Sentinel-2 and to see those differences. But again, we relied on taking the Venus data and effectively downsampling it to 10 meters. So we created another foundation model at 10-meter resolution. And this time, we used the encoder and decoder approach. So what we did was we were trying to forecast NDVI into the future. And what we did was we did that for the baseline model and then compared that to the 10-meter foundation model, but ran it at 5-meter resolution. And what we got was about a 24% change in NDVI signal. So it kind of intuitively makes sense that you have a little bit less information in the model and the surface reflectance might not be forecast quite as good. So in summary, we have some interesting results for the temporal and spatial resolution. They seem to make a difference for certain applications of forecasting, and we're going to continue to validate this model, build upon it, and we'd like to do some benchmarking. There was a great talk by Vito on Presto, so if we can actually bring the Presto model in here and compare it, that'd be a nice benchmark. We're also planning to share Venus data, so if other people want to use Venus for running dense time series analysis, building foundation models would be a great place to collaborate with us. And then we're launching in June, if I didn't mention that already, and we'll be using that data as part of this model. And then lastly, if anyone wants to collaborate on using our data or foundation model development, we'd love to connect. And thank you all very much for listening. Yeah, happy to take any questions.
So we have time for questions now. I'm going to start. Can you go back to slide 11 where you showed the comparison between the one before? So on this side, the one that you have less data, as you get closer to the harvest time from right to left, you see continuous improvement. So the smaller lead time helps. With the other one, it's kind of saturated. Any thought on what is happening there? So it's too much data in this case doesn't help, basically. The lead time doesn't matter in this case much.
Yeah, I think it might be relying on some average measures, so then you start getting these high fluctuations. It's hard to understand why it has those broad fluctuations, but you can see around that 50 mark, there's quite a large fluctuation. It could be a bit of data shortage. We did test on 1 million samples, but I think it's also just using averages maybe or something as opposed to really understanding the vegetation curves.
Okay, and this is all for 1 year in terms of seasonality?
Yeah, we trained on multiple years, and then we we did the testing on different years. So I think it was 2017 to 2019 or something like that. We trained on, then we did 2021 and 2022 for the testing. So,
okay. Thank you. Other questions? Now that we have time, no one has questions.
We have something online.
Oh, okay. Let's do that.
If you want. Online, they ask what is the gain of a masked autoencoder rather than a standard autoencoder in your study?
In our context, the masked autoencoder was useful because we were patching both in space and time. And so that just allowed us to do a lot of efficient training of pre-training, especially of the model. So because it was almost like a 3D patching of spatially and temporally, it worked well for our use case. I guess there's other ways to do it, but that was the technology that seemed to work the best for us.
Okay, thank you.
We have one question there, and that would be the final one. Yeah.
When you're forecasting, are you going single shot to the forecast data, or is this an autoregressive model that then basically is reapplied to itself to make a successive forecast?
The latter. Yeah.
Then thank you, Chris. Yeah, we'll move to the next speaker. Our next speaker is Mohana Diab, speaking on Lang RS, optimizing zero-shot semantic segmentation of remote sensing imagery. Yeah, please.
Good morning, everyone. Yeah, it works. So today I'm going to be presenting the Lang RS Python package. This is something I've developed during my master's thesis, so 1 year ago. This library, what it does is to optimize zero-shot detection. I'm going to show in a couple of slides exactly where that's coming from. I just want to show like a little bit of a roadmap of what we're going to do today. The first thing we're going to do is that we're going to go over the grounding dyno and the segment anything model used in this work. Then we're going to talk about some adaptations to remote sensing, the current implementation and their limitations, and our motives basically to doing this work. Then I'm going to talk about the pipeline, methodology, and the results. Finally, I'm going to talk about the latest advances and our future directions in this work. So to start things off, I just want to review the first two models we're going to use, the grounding dyno and the segment anything. So there's been a lot of talk about the dyno model in this conference, so you have been pretty exposed to the architecture. The difference with grounding dyno is that it is a grounded model, so it has open set detection. It can detect anything with natural language prompts, almost anything. It has a transformer architecture, and it's task agnostic, means that it has a very good zero-shot capability. Then we're going to talk about the SAM, which is the segment anything model developed by Meta AI. The good thing about this model is that it is promptable using points. So you can put a point on an object of interest, and it will try to segment that thing. You can also use masks. So you give a portion of a mask of something you want, and then it will try to find similar objects. Or you can use boxes, so bounding boxes, and it will try to segment what's inside these boxes. It has been trained on a segment anything 1 billion data set, so it's a data set of, I think, 1.1 million images with 1 billion masks. It's also transformer based, and it's also task agnostic, so it has pretty good zero-shot capabilities. So how does this relate to remote sensing? Well, a lot of research has been poured into this field that uses SAM. If you just hit SAM and remote sensing, you're going to find a lot of things. But the most relevant ones in our case is the first one is called the grounded SAM. So what they did in this paper is that they have introduced this concept of stacking grounding dyno and SAM on top of each other. So what it actually does is that it uses grounding dyno to, oops. Okay, it uses grounding dyno to detect what's ever in an image. So you give it a prompt, for example, in this image, you say, hey, can you detect a dog? It will put a bounding box on that dog. And then you give it to SAM with the input prompt of the box itself, so you don't have to do anything. You just give it the image and the bounding boxes, and it will segment what's inside pretty efficiently. The other thing I want to talk about is the usage of SAM for remote sensing applications. So in this paper, What they did is that they tried to do 0 shot and then 1 shot, and that was a major inspiration. So because we saw it has very good potential. In some modalities, they did use grounding lino, but mostly throughout their work, they used hand-grafted bounding boxes. So that was the start of, let's say, the spark in our work. So you can see that the segmentation capabilities are quite good for aerial images. Then we're going to go to the current implementations and where we start off. So for those who are familiar, there is a package called SamGeo. It's something that implements things out of the box. So it just puts grounding lino and SAM and implements them to SAM, to remote sensing imagery. It can identify geospatial formats, so TIFFs and shapefiles. And as you can see, in some cases, it has very good performance. But in other cases, such as the one I was trying to do, so in my thesis, in my early stages, I was trying to do this study where I was trying to count the number of vegetation or trees or whatever in bounding boxes and then try to estimate their density in terms of area size. But when I tried to use SamGeo, the results weren't that impressive. I will go to why in a bit, but you can see another example of how the segmentation mass is not really representative of what I'm trying to do. So how we fix this problem with our pipeline. So the pipeline that we have with LangRS, it takes an aerial image, so any remote sensing image, and a text prompt. And the outputs are bounding boxes and the segmentation masks. How it does that is that for the inputs, it does something called sliding aided hyperinference. So it's AHI for those who are aware of the concept. And then we calculate the area of the bounding box, and we'll go through why in a minute. Then we do some outlier rejection, and then we go to segmentation. This may seem a bit simple, but it actually works pretty well. So the first point is you take the same images that we did with SamGeo, and you did do something called sliding aided hyperinference. So what this is actually is that instead of running a full inference in the whole image, you just take a sliding window approach, and you do the inference on that specific window, and then you slide it to the right with some overlap region, and then you do the inference again. And what this does is that it does two things. First, reduce the computational overhead. So if you do a full inference, you feed the whole image, but when you do this, you have less inputs to the model. And the second thing it does is that it reduces the main issue of SamGeo. So if you can see it on the right, that is the SamGeo result. You can't really see it, but there's like a huge bounding box on the whole, the entirety of the image. Because it's a grounding model, when you say, okay, can you detect roofs, it will actually put a bounding box on the entire image because it's detecting roofs in the entire image. And you can see some other instances where there are very big bounding boxes that are covering entire areas instead of a single object. If you look to the left, that's not really present because you're doing it in smaller modalities, but the big bounding boxes are still present. So what we're trying to do is we're trying to reject these boxes. So what we really want is homogeneous distribution. So if you're trying to detect areas or objects with homogeneous area distribution, you're going to see that most of the objects lie in the horizontal, let's say, distribution, and you want to get rid of the long tail distribution, so the area on the right. And if you keep those and you reject the ones on the right, using some data-driven, simple, like classical machine learning algorithms. So first are statistical methods, such as z-score, interquartile range, robust covariance, and random forests. There are a total of 7. I also have SVM and SVM with SGD. And you remove these boxes, you get something closer to this. So now you can see that there are a lot of bounding boxes covering only the objects of interest and not anything else. So if you take this image and you do the segment anything model on it, you get something like this, which looks way better than the previous segmentation. So this is the current pipeline, methodology, and the results. Now I'm going to talk about the more things that we implemented ever since we published the first work. The first is adopting adaptive slicing aided hyperinference. So what it does is that for each prompt, it will try to adapt the window size so that you don't have to set it manually. The second thing is size-aware non-max suppression. The title is a bit misleading because non-max suppression deals with confidence score, and we're not really doing that. We're trying to adapt it to a size-aware. So instead of the confidence score, you insert either the inverse of the area or the area itself, depending on the application. And then we applied also SAHI for segmentation, which led in a 50% reduction. Here's the latest example of some areas. You can see that the results are actually quite nice. If you're interested in some benchmarking, you can check the original paper, which I will have the QR in a bit. We're testing with model quantization to reduce the overhead. Scale-aware SAHI, the same thing. And then we're developing a Hugging Face UI that everyone can use. By the way, this model can run on GitHub Collabs. You can run it also on your personal PC. It runs quite well. You can check the paper, the GitHub, and on the 22nd of May, so in a couple of weeks, we're doing a hands-on workshop in AI for Good, if anyone's interested. And thank you.
Questions?
I just wanted to ask whether in the grounding dyno prompt, you use any indications that these are satellite images? Did you try to guide it, or did you just use the class names?
So in the original paper, like for the grounding dyno, I tried doing long prompts, but the model goes crazy. Actually, in their implementation, they say that it performs better when you have like a single word prompts or maximum 2 words. In the original paper, we have some other prompts where you are trying to detect like only blue cars in the image, and it will successfully do that. But if you try longer prompts, it will just go crazy.
Any other questions?
As I understand, the purpose of your work is not what I asked, but did you conduct any adversarial tests or red team tests? I'm curious how the model performs under poisoned attacks. Like, I think it can be fooled easily with text attacks or like the image attacks.
What?
Did you perform any like adversarial test for this project, like red team tests for AI?
I'm sorry, I don't understand.
Adversarial test, I think he's asking about. Adversarial test, he's asking if you have conducted any adversarial tests.
No. We haven't tried poisoning any dataset whatsoever. I'm actually looking to benchmark it against some datasets right now to provide a better indicative of its performance. So no.
And maybe one more question. Have you developed any intuition of where this doesn't work and how well it translates between different biomes, geospatial?
Yeah. So basically, it works better when it works best when you have remote sensing images of less than 1 meter spatial resolution, so on very high resolution images. And the second thing is that it works in homogeneously distributed area sizes. So when you have objects of the same kind of area and they are distributed in the image, but if you're trying to detect some stuff that are of varying areas, sometimes it does not perform that well. It doesn't perform well with roads because like they have very different shapes and everything, and it's hard to detect them with an object detection model first.
Any other question? I have one. So when you use the distribution of the areas to cut basically outliers, how sensitive is that across a region? For example, if you're, I don't know, you have an urban area like Rome, you have high resolution imagery, you're doing building classification, and these small chips will have very heterogeneous landscapes and building sizes will be very different.
Yeah.
Based on your assessment, is it better to do this at the chip level? For each of them, you detect outliers, you do it across the whole region?
Yeah.
How sensitive is it?
Yeah, if you do it on a patch level, it's very sensitive because, as you said, like in a complete remote sensing image, patches can be very heterogeneous. But if you do it on the whole image, and that's actually the purpose of using a sliding window, is that if you do the sliding window on a single image, you don't have that much of a distribution. But if you do it on a whole image and then you group all these bounding boxes, now you have that distribution better. So to answer your question, no, I use it on a full image instead of patches.
But then how sensitive is that to like industrial buildings? Because then the bias would be at a city level, you will have very big like factories and buildings that can be biasing your distribution. that resolving, like removing those. I'm thinking basically this is very smart, but at the same time very sensitive to that.
Yeah. So the thing is, the area is a quadratic kind of thing. So depending on you will see it in the implementation. So the difference in the area between a house and a factory will be very decimal when you consider the whole area, like the big boxes that are available. So you will see that maybe there's a bump in the distribution, but in the long tail distribution, it will remove all of that. Also, you can use a majority vote in the entirety of the proposed machine learning algorithms to have a better vote. Yeah.
Thank you. If no further question, then let's thank our speaker. Thank you. And final speaker of this session, I think Yotam Gigi from Google. Yes. A remote sensing vision language foundation model for zero-shot tasks.
Hello. Hi. Just 1 second. Okay. Hi, I'm Yotam. I'm from Google. And I'm going to tell you all about the work that we have been doing on remote sensing foundation models with VLM, okay, Vision Language Foundation models. And this is a work that I've also been doing with George, that's sitting here, and with others in the team. And we can start talking about it. Okay. So first, let's explain what do I mean when I say Vision Language Foundation models. I think that all of you already know these models have revolutionized the AI, and specifically in vision. And the things that made them so interesting is the way now these models are able to solve problems without the need of dedicated training set. So if you want to take an image and you want to know if there is a cat or a dog in this image, in the past, you might have needed to create a data set specified for this, specifically for this task. And today, you can just take these data sets, not these data sets, these VLMs, okay, Visual Language Foundation models, and solve different types of problems, all of them together without the need of specific training. In the heart of these Visual Language Foundation models lies massive data sets of images and text aligned, okay, so massive. And these are the very reason that these models work so well on such a huge variety of tasks, even if these tasks are not text-related, right? If you want to tell between a cat and a dog, it's not a text-related task, but having a Visual Language Foundation model can help you with that. Great, so these are Vision Language Foundation models. Now, remote sensing images, and I will start with a very important note. When I say in this lecture remote sensing images, I mostly mean RGB images in various resolutions, okay? We didn't solve this problem also for hyperspectral yet. Having said that, even though these images still have RGB bands, right, they are very unique in their way, right? And they have, like, for example, they cover large areas, usually more than normal images that you just take with your camera. They have very different characteristics, and okay. And the very first thing that we notice is there are much less data sets of vision language for remote sensing. So if for normal images, like round level images, we can get to billions, data sets of billions of images with images and texts. For remote sensing, I think that it's of millions, okay, that you can get if you gather several data sets or something like that, that combine images and texts with high quality, okay? So this is a very important thing. And here comes our work. We wanted to address this bridge this gap by creating two novel data sets that we have created. They are complementary, so they are very different, and we're going to talk about each and every one of them. Unfortunately, they are private, so that we do not share them, obviously. What can we do? Happens, right? Anyway, we're going to describe how we created them, so this can help you. So, okay. So let's start with RS Landmarks. RS Landmarks has 18 million images How did we create it? So we used the Google images, these images that you can find in Google Earth, on Google Maps, remote sensing images, taking RGB images, and we created 18 million crops of these images. Okay, so we created many, many, many different images from these Google satellites, the Google images, and the first thing that we did is to align all the information from Google Maps on these images. So now we have 18 million images, and for every image, we have all the information in Google Maps on that image. What is the information in Google Maps? Obviously, you all have played with Google Maps. So you know that there are, like, I don't know, roads and buildings, okay, but there are also barber shops, fast food restaurants, shopping malls, many things that you can find in Google Maps. We have seen like thousands of different classes of things. So this is very rich information. We combined this, took all the images with all the information in Google Maps, and we gave all this information to Gemini. Now, Gemini has access both to the image and all the information from Google Maps, and we ask with the prompt, you know, from Gemini to create a nice flowing caption about this image that summarizes all the information, maybe even filters out things that cannot be seen from above. So Gemini eventually created for each and every one of these 18 million images, created a very nice caption that describes the image and also the information from Google Maps if it was relevant. Sometimes it's not relevant, also messy. Here is an example, okay, this is an image that we just found on the internet, not on the internet, sorry, from Google Maps, from the Google satellites. And this is information that we found from Google Maps, right? There is, apparently, this is an oil refinery, I wouldn't know that, right? And there is also some buildings and roads and stuff, so, okay, and this is what Gemini created. So that's nice, a nice caption. Okay. Next, we described RS landmarks. Now I'm describing the other data set. So if RS landmarks was 18 million, this one is 30 million. What is this data set, RS Webley? RS Webley, in order to understand it, we must understand first the Webley data set. This is another private Google data set, but Webley is a collection of images from the net, from just the internet, with alt texts. Okay, so it's a huge data set. It's roughly billions of images, something like that, with captions from the web. So all these images are called Webley. We said to ourselves, right, we thought, probably you can find there, you know, from the internet, some satellite images, right, some remote sensing images. So what we wanted to do and what we did is to create the RS Webley, which is we filtered Webley for satellite and for aerial images, remote sensing images. How did it do it? We started by, it's not trivial, right, to filter these billions of images and find only remote sensing images there. So we went through a roughly two-step process. First step, we manually labeled 800 images. We then gave it, we used the classifier. We trained the classifier on these few hundred images. We had this classifier. We used it to create a larger data set, 40K, and then we, again, manually, this time we used crowd compute, manually labeled remote sensing or not 40K images. And then, again, once we had a high-quality 40K data set, manually labeled, we, again, trained another classifier, which we used to filter the entire Webley, and we got to 30 million images. Now, one last critical step that we found to be very helpful is giving these images, again, to Gemini. So we take all these images from the web, we give them to Gemini, and again, ask Gemini to produce some nice some nice caption, okay? And then Gemini created a nicer caption. I would say that usually captions from the web are very messy, okay? Sometimes they don't even refer to the image, sometimes it's the file name, many different errors like that. So Gemini cleans everything and makes everything nicer, so nice. Okay, so we created this data set of 50 million images and text. How did we train a model? So we trained a clip model on this data set. I'll soon go into details, but first, clip is it's a well-known architecture, like image encoder, text encoder. We we require the image embedding and the text embedding to match if the image and text match. Okay, so we have a match loss. Specifically, to check that our datasets are indeed robust, we tried 2 different clip-based architectures, model architectures off the shelf, right? The left one is the SIGLIP. SIGLIP is the architecture. SIGLIP is unique by using sigmoid loss in addition to the clip architecture, and Mammoth, another architecture that is unique by also generating text. So it also combines, in addition to the clip loss, generative loss. Okay, and how did we evaluate? So we trained, very nice, and how did we evaluate eventually? We used, first, one of the tasks is zero-shot classification. What is zero-shot classification? We just take a classification dataset. For example, functional map of the world, or a ZISC, 45. We just took these classification datasets. This is very common, okay? And we wanted to test them in zero-shot with our models. So how did we do that? For every class, we generated a template sentence. For example, a remote sensing image of a class, okay? And then we found which of these sentences best matches the image, right? This is what the model can do, matches images and text. So we just checked which of the sentence. This is how we created this zero-shot classification. Another task that we evaluated is zero-shot retrieval. What is zero-shot retrieval? If in the previous, in the zero-shot classification, we used the classification dataset, here we used an image captions dataset. So there are such, for example, UCM captions. We have a set of images and a set of captions. And what we did is that we asked the model, again, it's standard, ask the model to match. So for every text, we want to match the best image, and we want this to be the image and the text that match, obviously. Okay, so we ask this, and we check how well the model does that. So we compare different models. These are the results that we have. We compare the first 3 rows here. First 3 rows are public vision language foundation models for remote sensing. The second 2 rows are baselines. So these are the SIGLIP and Mammoth that were not trained on remote sensing. And the last 3 rows are our models, the SIGLIP and Mammoth, that were trained on the remote sensing datasets that we created. And as you can see, there is a nice gap and between the baselines and also between the public benchmarks. And you can see that the huge gap between the baselines and our models, this is very nice because it means that our datasets indeed carry information. Okay, one last demo that I want to show you, not a demo, but the results of a demo, is okay, we try to see okay, what can this do? So we took 100 million images. Again, in Google, it's easier to create 100 million images dataset or something. So we took just random 100 million crops from the world, and we ran our model and created, and for every image we have now its embeddings, and we put it in an indexed image dataset. And now we could easily query for images from these. So this is the fact that we have 100 million images in the beginning allows us to find very interesting things. Okay, so we query it with text. So for example, drawing on a field. I really like this one, like the first one in the drawing on a field, but also there is a trademark on one of the fields. Someone drew a trademark. I was surprised. And I don't know, for example, pipes, just pipes lying around somewhere on Earth. We were able to find them. That's nice. Planes, mid-air, just flying, caught on the satellite, right? Things that you can just find when you have 100 million images, and also a model that allows nice searching. Craters, nice craters that we found. Corn maze, also nice. Ancient temple in the woods. I bet that some of them are not registered in Google Maps. We can just go there. Cherry blossom nuclear power plant, which is very distinctive. Whale-shaped building. I think that the first one is very nice. I never saw this, kind of like a better whale-shaped building. Fallen tree party. Sorry, I really spent too much time on that. It's so enjoyable. You can also ask for some more complex compositions. Wind turbine surrounded by ice. Go-kart. A whale, maybe? I'm not sure, but maybe this is a whale. That's it. That's the work.
Questions? You one there, and then.
Thank you for your talk. All what you treat is like object-centric. I agree that text is really good at describing an object-centric image, but in remote sensing is not mostly the case. Often we have like a diversity of information inside the image that we have to combine to get things. Do you have any evaluation on non-object-centric tasks or things like this?
I think that metrics, if you take the retrieval tasks, they are not object-centric. The retrieval data sets is just an image of something, not necessarily one thing, and then there is a caption that just describes the image. Just out of the, if I go back, sorry, so many slides, and to the table. So I think that this one is like non-object-centric, I hope. I hope that one day, here it is. Like the resict, UCM, and resitmed, I think that they are like less object-centric. So maybe it answers.
Thank you. I have a question about your pseudo-labeling pipeline, because there is something that I didn't understand. You said that you align the satellite and aerial imagery. And I don't really, I think it's the next slide. Yeah, so why do you need to do this? And what is actually being fed to Gemini? Is it either of these images, or is it the concatenation? You do put them in different channels?
No, sorry if I was confusing. There is only one image. Okay, there is not satellite and an aerial image, sorry. It's one image that we cropped. It's either satellite or aerial, right, as you can see in Google Maps. And this is the image that is fed to Gemini alongside with the facts, the map facts, yeah.
Cool. Thank you to the speaker. So we can continue the chat in the break. And please be back in the sessions, this one or the parallel one, at noon, so we'll continue that. Let's thank our speakers one more time.
All right, let's get started with the second half of the session. If I could please ask the first presenter to come up. We have a presentation on vision language models for EO regression, a go or no go.
Hello, everyone. I'm Xi Zhe. I'm now a postdoc working in the Technical Universities of Munich, and very happy to have a chance to show our recent exploration on whether VLMs can handle the scientific regression tasks in Earth observation. In the following times, I will first give a very brief introduction on the architectures and capabilities of vision language models, and then I will introduce the regression tasks in Earth observation and analyze the EO data's characteristics. And then, based on these fundamental knowledges, I will analyze the advantages, challenges, methodology insights, and the potential futures of using VLMs for regression tasks in EO. First, I will introduce the two popular VLM architectures in Earth observation. The first one is the contrastive VLMs, which are always in the CLIP architecture. The input is always the multi-sensor EO data, metadata, and the geolocations. And the second popular architectures is the next token prediction architectures, which is always conversational. And the representative work is the Lava series model. And compared with the contrastive models, conversational models can include more scientific domain knowledge because it can deal with long sentences in the language text. And I have given an example here. And compared these two kinds of the architectures, the contrastive architectures always focus on the embedding alignment. They always good at the zero-shot transferring, but the conventional VLMs always focusing on the instruction tuning on multimodality data, and they have strong ability in summarizing open-ended descriptions and some other tasks. Then I will give an introduction on the VLM capabilities of the SOTA method. So the SOTA method are always focusing on the description, generation, and reasoning and understanding tasks. All these tasks are based on the perception abilities, and some of the methods also have the abilities to do some detection tasks. But how about the regression task in EO? Because the scientific regression task is very important in the Earth observation, such as predicting the biometrics, climate, temperature, hydrology, oils, and other parameters. So can we pushing the boundaries of VLM capabilities in Earth observation? So vision language models have large potentials in handling the regression tasks in Earth observation, because the traditional method such as the unite and transformer-based method always only relying on the image modalities data. So there will be a information bottleneck. But for VLM models, it has the abilities to introduce some EO science knowledges, so the information bottleneck will be broken. So, for example, if we want to predict the biomass, if you only relying on the image modalities data, the information bottleneck will limit the performance. But if you use the vision language models, maybe you could include the geolocation, vegetarians, dominant species, and the soil parameters in the prediction. So the prediction may be more precise and accuracy. And then let's talk about the challenges of VLMs in regression tasks in EO. Because compared with the general data in the CV community, EO data is always from multi-sensors, so they will have a complex data structure. And for handling the regression task using the vision language data, up to now, the community still lacks the training data and comprehensive benchmark. So, and the second challenge is that from the representative level, there will be a misalignment between the numeric regression and the symbolic generation mechanism. Because if the traditional vision language models also always predict the text, so one token corresponding to one word. But if you predict a number, for example, if the predict value is 123, and one corresponding to a token, two corresponding to a token, and three also corresponding to a token, three tokens corresponding to one numeric value, that's will leading the result have no numeric meanings, just the symbolic meanings, which will challenge the prediction. And from the modeling level, errors will propagate in multi-steps numerical generation. For example, if the errors is in the three, it will be very large. But if the error prediction in the 5 in the slides, it will be very low. So that will be another challenge. And from the optimization level, for the SOTA method, there still lacks the direct numerical optimization method, because if you would like to predict a word, maybe the aim of the optimization is to minimize the likelihood of generating correct tokens. So the CE loss is always used. But for the regression task, you should minimizing the numeric errors. So MSE loss may be more available, maybe better. And here, according to the challenges and the characteristics of the EO data, and we give some inspirations in the model design. The first one is the very direct one, that is to do the parallel representation, separating the discrete and the continuous prediction. I mean, in one branch after the large language model to do the generation, and another branch to do the regression. And going further, if you want to share some information between these two branches, that may be better. And if you just want to have a more elegant architecture, maybe you could just use one branch. I mean, one head. This one head have MOE architecture, and different export in the MOE handles different tasks. Maybe one handles regression task, and one handles the generation task. And another architecture is that maybe we could do a discrete guidance architecture. There will still be two branches. The first branch is that the text generate branch. Maybe you could use this branch to just predict a very rough interval, and then input this information to discrete guide the regression's prediction, and maybe the regression branch will give the fine-grained result. And this is the second methodology insights, and we could reformulate the EO regression task as attribute map generation task, because all the input data, such as the EO data and the text, and the generated data, maybe the biomass and any other regression results, are all wave of the projection of the real physics world. So we give two waves, one text wave and one EO data wave. We want to generate another wave, maybe biomass, maybe any other things. So that we'll need attribute decoder. That decoder will be maybe the diffusion model, and maybe a visual auto-regressive model. That will be all fine. And the advantages of these models is that we can get a dense map that will be more precious than just getting a value. And last but not least, we can also do the probabilistic modeling, because the EO regression task always need a continuous prediction, but the VLM models is always in a discrete next prediction mechanism, so the probability models can serve as a bridge here. We just using the vision language models to predict the parameters of the mixture models, maybe the Gaussian mixture models, and then using these mixture models to predict the regression result instead of predicting the result directly. And here I will give some introduction of our recent work. We're building a benchmark to handling this question. This benchmark names the REO instruct, and here's the detailed information, which covers 4 kinds of dominologies, including land cover, ecology patch, biomass, and human activities. And contains 1.6 million EO data, and the modalities covers the RGB, multispectral, and SAR images. And then under this basis, we have designed a model, and as shown in the table 4, our model significantly outperforms the basic lava model, and we have also do some additional method experiment, and the result shows that our model still outperforms the traditional method like the RASNet and the UNITE. And here I give some potential future directions. Basically, we can give we can design more advanced model architecture, and maybe multi-temporal regression and multi-step regression is also needed. And because in some domains, the scientific questions has the inner link, maybe the connection with each other. So multi-domain regressions is also very deserved to explore. So for the scientific regressions, uncertainty quantification is also very important because reliable and trustworthy is needed in this domain. And in all, using the VLMs to handling the regression task is of great potentials and scientific significance, but there are still some challenges. If you're also interested in these topics and have any questions, please feel free to drop me an email and find me through the LinkedIn. Thanks. Thank you for listening.
Do we have any questions in the room?
Oh, we have one here, and then I will ask.
Thank you for your insightful talk. I would like to ask, so it's a go or a no-go, do you propose, again, using VLMs for regression tasks or taking more agentic approach to solve the problems related to estimating biomass or other stuff?
Oh, so I'm not catching your question. Could you repeat it? Yeah.
Sure.
Yeah.
So the question is basically, for regression tasks, there are many discrepancies, as you discussed, related to VLMs.
Yeah.
So do you still propose using VLMs for regression tasks, or you would opt for agentic approach, wherein different agents are solving the problem? We have specific models solving different problems.
Yeah, we have tried the tree-head prediction and the biomass problem with our method, but any other tasks have not been tried. Maybe in the future we will try this one. Yeah, we have tried just 2 tasks.
Sure, thanks.
So my question, can you go back 2 slides where you had the results of the different models in the table?
Yeah.
So the last 2 rows in the table are basically your model.
Yeah.
One has SAR, one doesn't have SAR.
Yeah.
Any insight why addition of SAR doesn't help with biomass? Because that's a little bit surprising, right? SAR usually gives a little bit of geometry, structure of vegetation, and so on. Is this, what type of biomass? Is this forest biomass? Is it very diverse? Why, any insight on basically why SAR didn't help?
Do you mean that why our models perform better than lava?
Yeah, I mean, basically the last 2 rows are very similar. I mean, the differences are marginal to some extent. And addition of SAR is not helping with the biomass estimation. Any insight on why?
Oh, I got your question. That's a very important question I've never shown in these slides, because this method is just a very basic one, so we do not directly processing the multispectral and the SAR images as its original, but instead we separate the multispectral image and the SAR image, and then transfer it into the RGB, into a pseudo RGB. I mean, I divided the multispectral into 3 bands, and then add the average band of the SAR, and then add them together. So I think the decrease comes from the very rough feature extraction, because we do not use the EO foundation model to get the feature embeddings. We just use the visual encoder from the general CV communities. So I think that will decrease the result, because we do not get the right information from the SAR, and then we combine it with the multispectral very roughly, I think.
All right, let's thank our speaker again. And on the note of SAR, we're now moving on to a presentation on foundation models for synthetic aperture radar.
Thank you. Hi, everyone. My name is Stian Norman Anfinsen. I'm the first author. I'm going to talk about foundation models for SAR. I'm not going to say anything about new models, and I won't give you any results. I'm just going to look back. On what has been done previously. I work for NORS, Norwegian Research Center in Tromsø, Norway. We work with a lot of different modalities, but mostly with SAR, with INSAR, with SAR oceanography, cryosphere remote sensing, and different things. And we haven't yet built a foundation model, but we want to. And when we do, we want to make sure that we treat our SAR data correctly and pay it the respect it should, because people throw a lot of different modalities to foundation models and treat them just like they were any kind of image bands. But SAR data, they are special. So our focus in this review is we want to look at how is SAR data being used in foundation models. Do foundation models do any kind of modality-specific pre-processing, augmentation, pre-training, pretext tasks? Should you do that? And the way to find out is that we've done this literature review, and hopefully at the other end we will get some insight, and I can give you some recommendations for future work. So, SAR can be used on its own. SAR can be used in a multimodal model. What do people say about SAR and about customizing things? Satellite imagery is a distinct modality and would therefore benefit from modality-specific frameworks and self-supervised learning tasks, says Lei and Karim Sadeh. Even more clearly, it says Li et al. That one of the fundamental challenges that need to be addressed is the ignorance of SAR characteristics in model design. But you also have people who say the opposite, that traditional models have been tailored to specific sensor data types. This specialization hinders holistic analysis that could benefit from the combined strength of diverse data sources. So some people, they actually want to make things more generic. So what's correct? I think all may be correct. It really depends on the context and what you're trying to achieve. But what's so special about SAR anyway? First of all, it has a very noise-like appearance, and it's due to this multiplicative, this speckle noise that follows this multiplicative signal model, which makes it very, very strong. You also have this side-looking SAR, this sensor geometry, which creates geometric distortions and artifacts. There's more than what hits the eye, the spatial information. You have a lot of information in the frequency domain, in the complex valued parts of the SAR signal. And you have a lot of special data formats like single-look complex, interferometric SAR, polarimetric SAR. You have the Sentinel-1 wave mode, and so on. So there's a lot of challenges here. The dilemma is, should we try to build something very, very generic, or should we build something bespoke? Multimodal or modality specific? I want to look at how SAR is being used in both cases. And I want to look at how important is it to be modality aware. And I hope that by reviewing these papers, I might get some answers, most of all empirically. Do we need any new augmentation methods, specifically for SAR? Should we try to adapt the pretext tasks to the downstream tasks, and to what extent? And finally, a question related to that. If you have pretext tasks that are trying to achieve like opposite goals, they are in conflict, what happens then, and what can you do? So now to the review. We have reviewed some 50 papers. What we searched for were papers on foundation models, both unimodal, SAR alone, and multimodal. With SAR, we looked at both new papers on new methods and overview survey papers. We looked at complete models trained from scratch and fine-tuned models. We also went to the more general deep learning literature for SAR to look at relevant representation learning methods. And also, we have read some fundamental papers on machine learning to try to answer some of the questions I listed. And here are my first conclusions. So the findings, in short, multimodal foundation models, they do not, in general, do anything to customize for SAR data. So dedicated SAR models, they sometimes do. I found 2 papers that suggest new augmentation methods, 4 that suggest new pretext tasks, 3 that do some kind of SAR-specific pre-training approach. And most of this customization is found in models for target recognition and pulsar data. I will look at some more details. So we have SAR-specific augmentation. First, in a paper on the WaveNet for the wave mode of Sentinel-1, where they experimented with some random notch filtering of the wave spectrum components in a contrastive learning approach. It didn't work, didn't improve things. Then you have Lee et al., who reviewed, when they were designing their SAR ATRX model for target recognition, they reviewed many augmentations, and some of those were related to vessel rotation prediction, some added Gaussian noise, to my surprise, and some used feature descriptors such as hog and gradients and such. Then you have Gallego Mejia et al., who limited themselves from using certain of the possible augmentations for SAR, which is understandable. Some years ago, I had a PhD student who were doing ship detection, and he refrained from rotating the SAR image and flipping it in certain directions, because in SAR you have range azimuth, which should not be swapped because it's easily detectable. And you have very particular noise models, and they are not Gaussian. For complex valued polarimetric SAR data, we have the ring mixture of expert model, which does not reconstruct ordinary pixel values, but the power of the polarimetric channels. Similarly, you have Wang et al., there's Pulsar model, and another unnamed model by another Wang et al. They reconstruct the scattering power of polarimetric decompositions. And I don't have the time to explain that to you, but it makes a lot of sense because there's a lot of physical information in that, so it's very interpretable. Then, in automatic target recognition with SAR data, I found in the references to one of these models, the ROT-ANET, which predicted the rotational patterns of vehicles. And for SAR image classification, there's a method that used contrastive learning between complex SAR image subfrequency features and deep amplitude image features to learn physical information. So there are some examples here. But let me go to the most interesting papers. In this SAR ATRX model for automatic target recognition is based on masked autoencoders. They actually note that masked autoencoding is very difficult for SAR. Then they review a lot of previous approaches to solve that problem, and that includes using frequency information, multi-stage training going gradually from ImageNet to SAR, or computing feature descriptors to suppress the noise and to enhance the target. And the chosen methodology is inspired by that because they initialized their masked autoencoder for SAR with natural image weights. And they also use multi-scale gradient features to suppress the speckle. So that's definitely a SAR-specific approach. A paper by Shi et al. On a similar topic. They build a vision language framework for few-shot target recognition. They also review a lot of papers that integrate frequency domain information with a goal of capturing robust and generalized feature, and they also build modules separately for extracting frequency domain information and to select the best polarimetric features. And that was all. That's what I found. So now, what's the status? Am I happy with this, and what should we do going forward? We see that most models cover amplitude data. I mean, that's the go-to SAR image modality to use in foundation models. There's one paper that uses coherence data. We see some papers working on pulsar data, complex pulsar data on a complex covariance matrix format, kind of specialized, not so important for practical or for operational use. And they all work on geocoded, georeferenced data. These models, they do not look at singular complex data, which in SAR we know is very, very important for many applications. They do not use the complex phase, interferometric phase, and they do not work in SAR sensor geometry. And the reason why I'm saying that is because we are actually at the moment building a model where we found it very useful to work in SAR geometry, because this is about SAR oceanography. Right. So, where should we start amending things? Frequency information is one of the things that were actually used by some of these papers that I've been looking at. It's rightfully so, because it has been proven important for target recognition, as I just told you. We know that the frequency domain contains a lot of important information about man-made targets, but could we do any better? There are loss functions in deep learning that are frequency aware. I had a PhD student working on just computing a simple FFT. That could be used in contrastive learning, trying to match patches, their spectrum. But using this, can we maybe move to some more general and elegant pretext tasks? And maybe can these be useful for more than just target recognition, characterization, detection, and so on, but also for other tasks? It will be interesting to see. Speckle has been handled. So we reviewed the model, SAR-W MixMay, which uses pixel-wise weighting to combat speckle. These target recognition models, they also mitigate speckle by the methods that I mentioned. However, there are things that should be exploited that are not being exploited. Del Sasso et al., they have done a lot of interesting work on speckle filtering. And lately, they also used despeckling as a pretext task when training the Merlin segmentation model, and that was very, very efficient. And that's one thing that I think we should try to incorporate in foundation models to learn SAR noise characteristics in a self-supervised fashion. Then you have the temporal information. SAR provides a lot of dense time series. Speckle is still an issue. I couldn't find any SAR-specific work on self-supervised learning that tries to make time-variant or time-invariant embeddings. So what I would be looking for would be SAR-specific versions of seasonal contrast, SECO, CACO, SATME, and other things that could support work with time series, because I think it's needed. The extension to spatial temporal models would be very timely, I would say. And one thing that crossed my mind when thinking about that, sometimes we need time invariance. Sometimes we actually need should I say the opposite, we need phenological information. And when you try to use pretext tasks that try to achieve both those things, that could be a conflict. And how do you handle that? I went to the more theoretical literature, the general machine learning literature, and there's a paper by Xiao et al., together with Efron and Trevor Durrell at Berkeley. So this is not the remote sensing papers, but they they write about how conflicting pretext tasks can be handled by using mixture of experts, by using separate embeddings. Finally, complex value data. We need foundation models for single or complex data. We need them for complex INSAR coherence. We do have a very nice paper by Abdallah et al. They use a multitask vision transformer for detecting, locating, and interpreting deformation from SAR interferograms. That's a very good starting point, but it's not a foundation model as I see it. They do not use semi-supervised learning. So we do need semi-supervised frameworks for complex data, SLC and INSAR phase. Conclusions. Foundation models for SAR, I would say they're in their infancy. Mostly, they treat SAR like any image. The target recognition models I looked at, they show that modality-specific approaches in exploiting frequency information, that's sufficient. Non-trivial SAR formats are not covered by the models. Methods from deep learning for SAR should be adopted and maybe extended and brought into use in foundation models. There are things like the Del Sasso paper, the despeckling pretext task that I mentioned. The end goal, in my view, should be to try to build multi-purpose models from different downstream tasks that jointly embed different invariances and variances using a lot of different pretext tasks that could potentially be in conflict. And to do so, we need to exploit methods such as mixture of experts and separate embedding spaces, which also have the benefit of making things more computational. That's all. Thank you.
Thank you. Really great research. I hope this is going to be published or is published because I would like to read it. So my question is, does it even make sense to make a single foundational model for SAR, given that SAR itself is such an umbrella term that often contains very irreconcilable data representation? And the second thing about the augmentation, yes, certain augmentations don't really make physical sense for SAR, but so is the case with the optical data, and people still use them because they help downstream tasks. So does it really matter that certain rotations don't make sense if it helps downstream tasks?
Those were several questions. Where should I start? Could you give me one cue? Sorry? Publication, not in the near future, but just contact me, and I'll try to provide some information. Yes. SAR is an umbrella term, so one model fits them all. I don't think that's going to happen. I would probably want to make, for example, a model for SAR oceanography or a model for SAR for INSAR, for example. Try to split it up because there are so different formats and so on to make it practical. So it would have to be more models, but they should all try to make use of domain knowledge. And sometimes things work. We don't even know why it works. This is a really, really empirical trade that we're in, which is sometimes a thing I really don't like. I think want things to be more theoretically founded. But I mean, if it works, why mend it? The proof is in the pudding.
Okay, I'm going to ask next. I mean, first, would love to chat more because we are building a SAR, Pulsar foundation model for P-band. So we can chat, and we are hitting some of those bullets, but not everything. So happy to see the summary. But I want to see your thoughts looking at the literature. You had a talk yesterday for a foundation model that was mapping basically multispectral bands to frequency, and then being agnostic to the basically frequency. Do you think something like that approach would be also valuable for SAR? Like we have P-band, C-band, L-band, X-band. We do that kind of transform because we have some of those overlapping limited airborne data from like pulsar data that have C-band, X-band, L-band. Do you think that is worth pursuing from what you have seen?
Are you referring to that paper by DAY2 and his postdoc? Sorry, I don't remember your name. I was talking to you yesterday.
Genja, yeah.
That was really interesting. I like that paper. I mean, I was in academia, and I would love to do things like that. But now I'm with a private research institute, and I'm focusing on things that are more operational. So then Sentinel-1 and 2 for me, that's the workhorses. So that's where I would go first, because that's how I get paid. But from a scientific point of view, yeah, great work by Davis and sorry, his postdoc. And that's something that should also be done, because we would like to be frequency agnostic in SAR, and I'm sure you can be.
You can be. Okay. So another research problem for the community. Thank you. This was a great review. So we are going to skip one of the talks. We don't have our presenter from ESA Lab, so we're going to move to the, I think, 5th presentation by Robert Kennedy. Is Robert around? Yes. Oh, wait. Sorry, I skipped one. Sorry, Robert. Too many lines here. So let's move to the presentation by Jazib Zafar. I skipped that one. Sorry for that. Foundation models for tree crown delineation.
Good afternoon, everyone. My name is Jazib Zafar. I'm a PhD student at the University of Göttingen. My research interests are deep learning for forest inventory, single tree detection, and what we're trying to do is trying to build a foundation model for forest remote sensing in general and tree crown delineation in particular. And we're at very early stages of it. And the reason I'm presenting to you today is to seek guidance and collaboration if any one of you is interested. First of all, there's different sensors in TCD. So, and going from highest resolution to the lowest resolution would be drones, where you get RGB information as well as maybe LiDAR point clouds. Canopy height model, infrared band at the GSD of maybe 1 to 10 centimeters, but which is limited by really small plot sizes because it does not scale very well unless you have a lot of resources. At a level above this is the aerial imagery, which certain subnational or national administrations do semi-regularly, is flight campaigns, which have a resolution of 10 to 100 centimeters, with a revisit time of 1 to 2 years. At a higher level would then be very high resolution satellites, which give you a lot of spectral information at rather low resolution, which of 30 centimeters to 3,400 centimeters, which has limited utility for tree crown delineation. And then finally, we have SAR bands such with sentinel imagery, etc., which don't directly help you with tree crown delineation, but can be useful for canopy structure and can be used as a proxy for canopy height. And as the spatial scale changes, the data homogeneity changes as well. So when you have really small spatial scale of data, for example, with the single plot data using UAV imagery, you have a highly homogeneous data, and by data homogeneity, I mean that the trees look similar and the number of features are a bit more compact, compared to when you scale it to global or national or subnational level data using satellites or aerial imagery. You have data that does not just include trees, but maybe other objects, for example, streets, water bodies, buildings, etc. And then also with trees which look very different to each other. An extreme example would that be a tree, or a tree in Norway might look very different to a tree in Brazil. would look very different to a palm oil plantation in Indonesia. And this complexity of features increases as the scale, spatial scale increases too. So why is there a need for remote sensing foundation models in tree crown detection? First of all, because we have a lot of sensor data with very different information sources. So we have 10 centimeter aerial imagery, 20 centimeter aerial imagery, 2 centimeter drone imagery, I don't know, 50 centimeter satellite imagery. And so it's one approach would be to have models trained on, separate models trained on all of these different data modalities, which is something that's been going on in the literature right now. If you look at the tree crown detection, tree crown delineation literature, that's what they're doing. And there's and this just means that there's a lot of distributed models that may or may not generalize. And to build really generalizable models, we kind of need to bring everything together. Furthermore, multi-temporal imagery is always not available maybe, and that is useful for tree crown delineation. And the downstream annotated data sets are very sparse, and they're very expensive to build. So what few data sets that we have, they could really benefit from having pre-trained backbones that already know a lot of important features that can then be used to further improve the performance on the small-scale data sets that individual groups or departments, universities, et cetera, are able to acquire. So I'll give you a motivating example. This all started with pre-training some resonant and vision transformer backbones using 10 centimeter RGB and IR orthophotos from North Rhine-Westphalia region of Germany, as well as FLAIR dataset from France. And we used DAY2 because everyone else was using masked autoencoders. So, and then the downstream task we selected was semantic segmentation with OAM TCD. OAM TCD is a data set that was released, I would believe, last year by Open Aerial Maps. It's a global data set at 10 centimeter resolution, and that gives segmentation masks for either single trees or a group of trees. And a few insights that we had was that models which were trained on data from France and Germany seemed to generalize pretty well to a global data set, and that there was minute differences between the architectures. So using ResNets versus vision transformers, at least in our case, did not lead to a significant difference in performance, at least on this data set. And I would just like to show you an example of a test tile which is not from Europe, trained on data from France and Germany, with the ground truth mask and the probability map and binarized mask using ResNet 50 and with small. The reason I chose to show these two architectures is because they have a comparable number of parameters, about 24 to 26 million. Their IOU is similar, of 0.81 for ResNet 50 and 0.83 for bit small. And the probability masks as well as the binarized masks, they look pretty good. And this kind of led us to be a bit more ambitious about what we were doing. So we decided to be okay, let's get as much data as we can, try to compile as many downstream data sets as we could find, and try to make a multimodal backbone. And we settled for DOFA. As I think someone had a presentation yesterday, talked about that we have a lot of different modalities, but the thing in common between all of them is that they're on electromagnetic spectrum. And that is why DOFA uses wavelengths as like the unifying thing to build these backbones at the patch embedding level. This is in comparison to, or like in contrast to something like FOMO Bench, which treats each band separately as a token, which we believe kind of fails to capture the complex interplay of relationships between different bands. So we're using the open aerial map dataset for very high resolution optical imagery, along with DOP imagery, LiDAR imagery, some worldview imagery that we have from other projects, and some low resolution SAR datasets. And then the downstream tasks include TCD, tree crown delineation, canopy height estimation, multi-class segmentation, also channel simulation. Like one of the earlier presentations talked about generating NIR band using RGB imagery. It's something we are also trying to attempt. We found the following downstream tree crown delineation datasets. This is not an exhaustive list, and we're still trying to build more, more downstream datasets. So we have neon tree evaluation, which is based on the neon sites in the United States. It's an instant segmentation dataset, has RGB, LiDAR, and hyperspectral data. We have BAM forests from Bavaria in Germany, which is very high resolution at 1.6 to 1.8 centimeter. It's a UAV dataset. And it has, I think, just RGB. Then we have Fortress from Baden-Württemberg, from around the Freiburg region in Germany, which is multi-class segmentation, multi-class semantic segmentation, which is probably the only data at this resolution that we could find, which contains RGB and normalized DSM. Then we have, of course, the OMTCD, which is like the main data set that we're looking at, because it's one semantic segmentation, but also like it's global. And Quebec trees, which is from Canada, and California urban trees data set. And the reason we're using this is because it's much lower resolution at 60 centimeters, has 4 bands, but has like point annotations, so we can actually detect single trees. The challenges are significant. It's a very challenging task. I'll point out a few challenges. First of all is like handling phenology in imagery. And some of you might have noticed that trees in February look different than trees in July, right? Because of like off-leaf, on-leaf difference. And if you build a model that's really good at detecting like tree crowns in leaf-on season, does that also work well in leaf-off season? If you were to train a model with tree images in July, do you think it would also perform as well if you were to take data in February? So that's something we have to incorporate. Data annotations for TCD are expensive and sparse. It's difficult to find higher resolution data, and it's difficult to annotate that data because you have to sometimes actually go out in the field, and not every lab or organization or government is willing to share their field data. And even if they do, sometimes they don't share the location of the plots. So it's difficult to get your hands on good quality annotated data. Sometimes telling apart one tree is difficult in a dense enough canopy. And because like trees have this self-similar structure in that like one part of a tree could look exactly like an entire tree. So it's really difficult to see, okay, where one tree ends and the next one begins. And validation on large spatial scales is also difficult because just the data is so sparse. So our future work is we'll finish training and publish the weights for both unimodal and multimodal approaches. We'll see if and what modalities that we can add more to it to improve performance further, as well as like any data augmentations that we could do that would help us more with the downstream performance. The main reason I'm here is to build more collaborations with you guys because you have a lot of experience training these foundation models. And we're planning a deep tree symposium in Leipzig if one of you would be interested in joining. And finally, we want to publish work because that's probably the most important thing to do. And with that, I finish my presentation. My name is Jazib Zafar, and thank you, everyone.
Time for 1 or 2 questions.
I think maybe I missed this. Can you talk a bit more about, so you were mentioning these 6 different data sets. Have you already done fine-tuning for them? Do you fine-tune on all of them together or separately? And if it's separate, do you have you looked at, or are you planning on looking at spatial generalizability from across the different regions? As you said, there's lots of challenges with vegetation and trees. Yeah.
So far, we're looking at like each of these separately. But like if we were able to have like something that generalizes even more, because the thing also is that the annotated data that we have is overwhelmingly from either Europe or North America, and mainly because like the groups and the institutions have more resources to collect that data, and so even if we're able to spatially generalize it, it would still be limited by the data that we have. Like it would be difficult to generalize to, let's say, Brazil with like Amazon or like Southeast Asia with the rainforests there. Yeah. I hope I answered your question.
We have one more question there.
Thank you. Have you done like a bit of an ablation study where you maybe tested just on the data sets that have similar resolutions? Because I mean, on the one hand, clumping together all of these data sets with like the different resolutions from like centimeter to like meter resolutions gives you a lot more like training data. But on the other hand, these sensors are so disparate. Like, do you have an idea if it helps to train across all of them, or do you think it helps to build like more specialized models for each of these cases?
I think it would be too early to tell at the moment. But so far with our results, it seems like resolution does play an important role in the downstream performance. And so that's why we're focusing mainly on higher resolution, like 20 centimeters or less, 20 centimeters or more, like 20 centimeters, 10 centimeters, and so on for this task.
Cool, thanks.
Yeah.
Awesome. Thank you. Let's thank our speaker.
Thank you very much.
So as I mentioned earlier, we're going to skip the talk by our ESA Lab colleagues and move to the presentation by Robert Kennedy on geospatial foundation models, slayers of the beasts of change.
Hi, everyone. I came from Oregon, all the way here. Although I know there's somebody who came all the way from Australia, so I'm not the most jet lagged. Thank you all for being here. And by the way, thanks to the organizers for having so many early career folks. Actually, let's give a hand to all the students, please, because you guys are great. It's very inspiring. I definitely feel like the old guy trying to keep up with this stuff, but it's fun, So, Slayers of the Beast of Change. This is folks in Oregon, also Spatial Informatics Group. We've got some collaborators in NASA and Google. So I can figure this out. Okay. So what do I mean by change? I'm talking about change in the Earth system. This ultimately is what a lot of us care about, right? It's the stuff that causes change that we like or don't like. And if we characterize that really well, we can measure impacts, we can infer a process. Ideally, we can do something to make the world a better place, right? So change detection, in terms of characterizing this, labeling it, understanding it is really critical. There's lots of different kinds of change. So if you look at any surface property over time, you can imagine like tree cover or impervious surface. There's lots of different things that can happen over time. The temporal dimension is obviously really critical. But if we just look at 2 dates, we look at these 2 images, I bet you can probably guess what's going on here. If I do a difference image, it'll probably help, right? So this is a fire in the forest. I don't really even have to tell you like the color scheme to you kind of know this. But I will draw your attention to all the other colors of stuff going on besides the fire. So there's that. So let's do the same thing here. Just right nearby. Do you see the change? I don't see the change. I barely even see the change here, but it's right there. And it's important. It says forest insect causing mortality. And it's a really important process in our forest, for example. And this level of subtlety needs to be captured, but it's really tricky, right? So we're continually trying to find better ways to do this. The issue, as a lot of you know, in change detection is that a lot of these things are very subtle. There's a lot of other non-interesting change that we consider noise. So what we've done forever is time series stuff with Landtrender. There's lots of good time series, pixel level time series approaches. You can label when stuff happens per pixel. Let's see here, come on. And then patchify that, put a human in, train on the shape, et cetera. And you can say that was forest management, that was urbanization, et cetera. But this is unsatisfying because if you get it wrong at the first step, you miss it in the second step. It'd be really nice if we could find something that these changes don't fit into the per pixel method. So we've been looking for non-per pixel methods. And so we're hoping that some contextual information would really make this task better, both for detection and for what I call attribution, which is labeling what caused it. And certainly the context we would think would be helpful here. So when we heard about foundation models, I'm not a foundation model person. I can't do all the cool diagrams you all do, which is really daunting and fun. But these components of what we understood about foundation models were very attractive. Our data sets are really expensive, so we don't have a lot of samples. So we need few-shot learning, and we want that contextual awareness. So we've been trying this for the last 1.5 years, and the Prithvi folks have been very generous working with us, trying to help us learn how to do this, the Google folks as well. So I'm going to talk a little bit about each one of these, sort of where we are in our learning journey with this. And just like the last speaker, I'm looking for other folks who've done this. Probably some of you have done this better, and I want to hear about that. But it's still very ripe territory. We have a great training data set for this. We have lots of different ones, but for this talk, I'm going to focus on this one because humans have actually looked at hundreds of thousands of polygons. They were detected with our normal approach, but they're labeled. And so we're going to treat them in slightly different ways here, which I won't belabor, but it's the same basic data set in the Great Lakes region of the US. And we were just asking some very basic questions about how to take something like Prithvi and put it into the change detection paradigm. And so we're sort of breaking the rules in the way we're setting up the imagery. We're not looking at 4 images within 1 year, but across 4 years, before and after, bracketing the change in different ways. We're also comparing this to just sort of a vanilla UNet. We've got frozen, unfrozen, random initializations for the weights. And the idea there is that if Prithvi's really learned something about the change, then hopefully the frozen or the unfrozen one will do way better than the random one. And then similarly, in terms of architecture, does the transformer approach work better than the UNet approach? And the answer initially to me is, wow, they're kind of all very similar if we look at the variety of different scores. And both 2 images before and 1 image before and after, and not, to me, a substantial difference. I would love to be able, I don't know how we do this, but I would love to see like error bars and all these things, right? I feel like that would be really helpful for comparing these models. But anyway, that's just an editorial aside. But if you look at the loss functions, this is actually kind of interesting. Indeed, the unfrozen and frozen Prithvi do better than the random, thank goodness. But the unfrozen one slightly outperforms this. Again, I don't know if this is significant, but it's consistent across a bunch of runs. We've done like 150 different runs. It's crazy. So this is just a few selected ones. But so this does suggest that what Prithvi's learned is helpful, and then the training on our own local data set further helps that a little. In terms of actual pictures, I have to I have to look at pictures to see if these things work. I can't just look at those lost graphs. So clear cuts seem to work pretty well. So this is just one of it's the frozen Prithvi and then the UNet. The annotation is what we have from our attribution data set. Works pretty well. However, a subtler change is tricky. And nobody really gets that very well. And in fact, I wonder if the way that we're scoring some of these metrics really penalizes this kind of situation enough. But that's maybe some of you have some insights into that too. We asked a few other questions, which I won't show a bunch of results for, but looked at different sizes of chip sizes. Didn't really seem to affect things. There were some differences in the learning rates. We also took out the time encoding, so we just sort of like subtracted the embeddings basically and then ran those through ahead and to the labeling process. And that didn't drastically change things. So the takeaway that I have at least is that they were very similar. Others do well on this task, but the global Prithvi trained locally, essentially the unfrozen one, works slightly better, but the subtle change is still very hard. So we still have a lot to figure out here. Scale, time coding, number of images, none of that seemed to matter. Standard recipe was fine. I mean, that's encouraging, right? This took us a lot of time, and I had a computer science person who knows what he's doing working with me, thank goodness. And so this was not for the faint of heart, but I think that if we have all these recipes eventually, sort of codified, that this could be done more efficiently with someone with sort of an intermediate CS background. Okay, I'm going to switch to the Google embedding fields. Kind of a different paradigm, but also embeddings, sort of encoding. And this was a different Google DeepMind group working with the Earth Engine folks. And they're releasing this as a paper. There's like beta versions you can get of this stuff if you're working with the Earth Engine team. But they're releasing this very soon, and they'll have all the details. I don't even know all the details, but they've embedded, they've brought in a bunch of different imagery and Jedi and weather, et cetera, in all their embeddings. These are 64 length embedding vectors, but they're at the 10-meter scale. At the 10-meter scale. So that's super critical for our remote sensing-y way of looking at the world, because we can look at a point, which is where a lot of our training data historically have come from, right? And they've got, as I said, they've embedded a bunch of stuff. The general structure we looked at here was following their lead. Okay, we've got embedding. We want to look at change between 2 years. We take the embedding fields from those 2 years and compare them somehow, combine them in some way through a classifier, compare that with reference data we get from people, and make a change attribution map. The question is how to combine them, right? And so we've got a bunch of, I won't go into all the details here, but we've got a bunch of different flavors of taking the same basic embedding fields and connecting them, subtracting them, doing dot product. Or, on the lower right, taking one of the reference years and then adding a difference image or a dot product. And the point of that is that you're drawing attention to the change with the difference image, but you're also anchoring it in space, because a change vector just floating out in space can mean quite different things depending on where it starts. Right, so this is like old school change vector stuff for those, like if you are able to get papers from the 90s, it says this kind of stuff. So this is very busy, but just for orientation, we got some reference images on the left. The 4 upper right quadrants are different flavors of these same embedding field difference images. The one on the lower right is just the dot product, and the one on the bottom middle is just kind of a visualization of the embedding fields themselves as a difference image. The point here simply is that, oh my gosh, there's a ton of difference. We're starting with the same raw material and just stacking it different ways. We got the same number of training points. Everything is the same, and there's that much difference. The legend is over there on the lower left. Harvest is in yellow. Development is in red. Apologize, I just realized for red-green colorblind folks, I'm sorry. We zoom in on a couple places. Lots of over-prediction in this particular case of Harvest. So what we've done here is we've sort of done an iterative training cycle to get our both change and no change classes. So we only have like 100 points here. So this is still very much few-shot learning. But we also found that the balance between stable and change classes drastically affected this as well. If we zoom in on, it works pretty well in some cases for sure. So this is like the top middle graph, the reference plus delta, that's that reference image plus the difference between the two. That worked great here, right? So just for fun, we did a standard accuracy assessment with randomized stratified random design. just to get a first cut, don't quote this, don't diss on the Google folks for this. This is just us trying to get a sense of how things are working. But we saw that there's still a lot of confusion, a lot of commission and omission across these different classes. I don't need to call it any particular one, but I do recommend, I would love to see in all of our talks eventually that we make maps, because that's ultimately, like, it's great, we need to compare on the chips, but we need to make maps and then test the maps. So from the perspective of the Google embedding fields, the ease of use is super, it's high ease of, they're easy to use. And it fits into the classic remote sensing training and testing approaches. I think that the structure to compare them across years still needs work. And maybe we need to do a time series approach on the embedding fields, I don't know. But they only go back to 2017 right now. And then it's very sensitive to the classifier, to the balance of change and no change, et cetera. So there's still a lot of work to do here. But if you're at all interested in this kind of thing, the Google folks are very happy to share this. And the Prithvi folks are, I don't know if Sujit's back in the room, but also super helpful. So it's been really fun to be in this, and just as, I don't know if we've slayed the beast of change yet. I would guess no, maybe a little bit. But we have a lot of good questions now, which is always fun academically. How do we represent the spatial patterns of uncertainty in those predictions? Didn't even talk about that at all. It's like my favorite thing right now is uncertainty, but this is really critical, and I think this is not just a problem, it can be an opportunity for us to think about how to compare across different maps if we frame it in an uncertainty lens. How do we look at uncertainty in the training labels? We definitely ran into that with our labeled chips for the Prithvi data. We have things that are just missing, and we're telling the model, we're not ignoring it because we don't know how to ignore it. We're saying everything that isn't a clear cut is interesting, but it's not a clear cut. And then it says, well, that looks the same as the clear cut. So it gets confused. And then this is a classic case of working with a minority class, right? It's very small on the landscape at any given moment. So are we doing the right performance metrics? Again, I'd love to get insight from folks. And there's a picture from Oregon. Thank you.
Thank you, Robert. We were talking about maps in the morning break that we didn't see any maps from any presentation, so thank you for showing that.
I showed some maps.
We have a question in the front. Can you bring the mic?
Yeah, hi. Thank you very much for this very interesting talk. I have a question to the first part, where you showed that the difference between different models was very minor. Do you have a publication for that? Because we are facing kind of the same problem, and we would like to have a confirmation that we are not the only one facing this problem, and maybe reference it.
We can join the Models Don't Differ Club. No, not yet. This is brand new. I mean, we haven't written this up. We are aiming to as fast as we can. Yeah, but maybe we should talk after. We can have a commiseration party about that. But yeah, I would love to hear more about other folks' experience with this as well. So.
Okay, thank you.
Other questions?
I would love to ask a follow-up question on this.
Yes. I was like, where is that voice? Okay.
I think this is like super nice. I'm not a big fan of lumping everything into one metric. So I'm wondering if you have looked at like spatial biases at all to test if there's any nuance in these models across spatial scales. And also, I mean, there will be examples that are harder and easier. So if you have developed any intuition on how some of these, I mean, freezing, not freezing trainings from scratch, is there anything that is learned there?
That's very gracious of you to think I've developed any intuition about this yet. I don't think I have, but we are definitely, the next thing that is, well, we want to look at the spatial patterns of this disagreement. I think that's part of what you're saying. And like, for example, it'd be really interesting to just to score every one of our patches and then map that metric just in a blocky way across the whole landscape and see where some of this is worse and better in both of these cases, honestly. And then make a map. The other thing is that I don't know, if we make a map with any of the chip-based approaches, I'm really super curious how much we're going to see artifacts of the chips, et cetera. So
we need post-processing, yeah.
What's that?
We need post-processing after that, yeah.
Yeah.
I also have a question. So, I mean, I know more about Prithvi than the Google one, so maybe I'll focus there. The fact that it has a hard time detecting those subtle changes, you think it relates, maybe the answer is in the question, but I want to get your thoughts, in the fact that in the pre-training data, we don't have long time series that includes those changes.
Right.
We sample individual year data for each location. Do you think that impacts and how we should go after that? Because that means we need like 10 times more data in our pre-training then.
Right.
Or we need specific models for change detection. I mean, pre-trained models.
Well, that I don't know, but you know, in my darker moments, I think, yeah, we need a bespoke change detection model. I don't know. I mean, I'm sure Paolo and the rest of the group would not want to draw another 100 million samples or whatever from the planet, but I think, I mean, I guess it does speak to the question, and I don't know the answer. I'm not sure how we know that. Some smart young person can figure this out, how we test whether 4 images within 1 year does capture the domain of change space that we're trying to ask it to figure out here. Because I think what you're saying is that if it's never seen anything like this, how can we expect it to know that? That's not fair, right? Is that kind of where you're
That's kind of my, yeah.
Yeah, I think that could be the case, for sure, yeah.
Any final thoughts or questions? This is our last presentation, by the way. We don't have the last person, so after this, it's lunch. We have one here. And
we
here.
freed up.
Let's
Okay.
capture both of these and then we'll close.
Okay, so I will start. So first of all, thank you. And I have a curiosity about the last slide because you mentioned the minority classes. And as this is also one of my problems, how to deal with them. I want to understand if you have a strategy to suggest, or is just we're putting there minority classes, it's a problem, but you don't have a solution till now.
Okay, right. You shouldn't just name problems, no solutions, yeah. Well, so from our so we've been dealing with this as an issue in our change detection world all the time. And so the way that the community has, and it's important, for example, with like forest reporting for UN agreements, right? Like how much you're losing. So the standard method there is to use a design-based sample approach, stratify on your minority classes, and so that you get an estimate of the area of this, of the minority class. There are, so the Olafson approach for accuracy assessment is the thing to do in that case, Stamen and Olafson and that whole mafia. And that's great, but we also know that there are problems with that, because if you have false negatives out in your non-change class, then that balloons up your estimate of your, so there aren't ever great solutions. I feel like it's, you just have to kind of eat around the edges to minimize it in your case. I don't know how that applies here though, with the loss metrics that we use on these chips. I guess I don't know the answer to that yet. So I can do it when we make a map, but when we're working with scoring them and penalizing them appropriately in the actual training or in the fine-tuning, I don't have a great answer. I'm sorry.
Yeah. Okay.
Okay.
Me either.
We can have another commiseration club. Lots. Yeah.
At least we are two with no answers.
Right.
Okay. Good.
Yeah.
We are creating a community of people with no answers at the moment.
Right.
Finding for answers for the future.
Right. Sign me up, please.
Adding a little bit more to the uncertainty, and this is a comment, not a question, and a thought experiment together with you. So what we have is the self-supervised learning regime. We also have the supervised learning regime, which is in the past, and we don't have the labeled data for it. There is something in between that is less attended to, I would say, and that's unsupervised learning schema as well. For instance, in your case, taking a look at novelty detection or anomaly detection when it comes to this specific approach, I don't have the answer at all for your problem, but this is also a thought experiment, meaning that if we want to choose the approach, why not looking at the entire spectrum of the solution? Why going either for completely self-supervised or completely supervised approach?
Okay. Yeah, I think I see what you're saying. I might need to have you help me out a little bit after that. But I think, well, the way that I was thinking of the uncertainty lens I think wasn't quite as advanced as that, but it was more from the perspective of essentially trying to make a map of the uncertainty. And there was a talk actually in the other session earlier this morning about this. And we do this a lot in the remote sensing world, but the problem there, or not a lot, but some, is that when we generate those uncertainty maps, they're usually just a slice of the overall uncertainty. It's the stuff we can we can do by jittering our models, for example, or changing our structure or parameters, but we don't know if it really does bracket the actual unknown answer or not, and that's ultimately what I'd like to get at. But I think that's slightly different than what you're saying, so I'll have to follow up with you. So.
I would be glad.
Okay, thanks.
Awesome.
People are peeling off like flies, so we should probably stop.
I think, yeah, it's time
Thank
for
you,
lunch.
everyone.
Thank you, everyone. Let's have lunch and then be back at the poster hall. At 2:30, poster session will start. Yeah, thanks to all our speakers.
Can we have our first speaker come up? We'll start in a couple minutes.
To meet you. I don't know when the slides. Okay.
It will be hectic to take it.
Oh, that's right.
Hi, everyone. I'm Philip. Bear with me in this last session and with us. I will try to be as clear as possible and as brief. I come from the Joint Research Center of the European Commission. We are based in the north of Italy, in Ispra, on the beautiful Lake Maggiore. I work with my colleagues in the food security unit, and this work has been done with also collaborations from University of Valencia. And it's about the application of a TAB-PFN, the Tabular Foundation Model, to crop yield forecasting in South Africa. Unlike the previous presentations where you had a lot of data, a lot of Earth observation data, and you used large models, unlike this, you could use large models, but in this case it's a bit difficult because this is a small data problem. And why is it important? The crop yield forecasting at national, subnational level are important for import-export decisions, for food security, if the production is lacking in several countries, so to provide also humanitarian aid. And also the more developed countries like US and West Europe, they have already their operational systems developed. So in these cases, it's not so necessary to do the operational yield forecasting in those countries. But in the countries where the data is usually lacking and there is not much crop statistics, then there is usually a problem also with food security and crop production. So recently, there were a lot of deep learning models used also for crop yield forecasting tasks. However, they were not outperforming significantly the more simple machine learning models like tree-based models or Gaussian regression or other decision tree models. This is due to the data size. So you see first at subnational level, there is more data depending on the country and the region. So, this is usually, it's a time series task. So for example, for 20 years, you have regional data per country, but still it's quite a small data set. Then if you go to the national level, it's also even worse, the data size problem. So you have practically one observed value per year for around 20 years if you want to use remote sensing data. So it's quite a poor data region. This can be done also at farm level or pixel level, but it's rarely the case that this data is available. Maybe in the US or France or Netherlands there is this data, but usually it's not the case in, for example, in African countries. So the goal of this study is to see if a foundational model could be used against our machine learning pipelines, which are tailored for crop yield forecasting. And this is a study based on subnational data set provided by the country, by South Africa. This data is also publicly available, so you can go to the website and download this data. And these are some of our papers that we use where we evaluated the machine learning models and also deep learning models for crop yield forecasting in Algeria. This is the study area and the crops, the main crops observed that is monitored. Maize is the main crop in South Africa. Around 50% of cropped area belongs to maize. The others are around 15 to 20%. Wheat is a winter crop, so it was not part of this study. Wheat, usually it's a rain-fed agriculture, so it's prone to climatic variability. And this is what we aim to capture with these models. The start of the season is around October, and the end of the season is in May. I said about the official yield statistics, it comes from the Crop Estimates Committee, and this is from 2001 to 2023 for 6 to 8 regions, depending on the crop. And yes, this is the ASAP data, the input features that we have used. This data is also publicly available. You can go to our website, you can download the rasters. Also, you can download the CSV files per region or per country at GAL1, GAL0, and GAL2. You see the source of the data. I'm over time. It's from MODIS from 2001, and we also we are switching to FAPAR, fractional photosynthetically absorbed radiation. We are switching to FAPAR to ensure operational continuity because the MODIS sensor is dying. It's nearing the end of its life, so we are switching to VIRS. We are already ready to switch to VIRS, so this is the reason, one of the reasons the FAPAR, and it's highly correlated with NDVI. We also use soil moisture and weather data from ECMWF and CHIRPS. And we use some auxiliary data like crop mask from World Cereal, Region ID, and Yield Trend. This data is available every 10 days, but we are aggregating spatially using crop mask from World Cereal. We are aggregating the data at the province level, at the region level, and we are also aggregating it temporarily. So for each month, we extract several features. And we use this in the machine learning workflows. This is the maximum data size that you see, around 184 samples for maize, and then lower for other crops. This is the foundation model that was published in January. It comes from the University of Freiburg, so made in Europe. It's it's published in Nature, and it's based on the prior data fitted network, so it was trained on the synthetically generated data, and it's a transformer, and it performs this in-context learning, so it's a zero-shot model. Somebody said in the previous presentation that it's task agnostic, and yes, so it's I like this definition. They also have a they started a private company called Prior Labs, and they recently raised around 9 million euros, so there is a huge interest behind this. They outperformed the classical decision trees, or also they used, against also support vector regression, they had better performance on their test benchmarks. And as they say, it's suited for small tabular data, up to 10,000 samples and 500 features. There is one more option for TAB-PFN, which is post-hoc ensemble. It's used to tune the TAB-PFN to a specific task, and it uses model ensembling and uses several forward passes. These are the baselines that we evaluated the TAB-PFN against. So simple lasso linear model, then kernel-based like Gaussian process regression and support vector regression, and popular tree-based models like XGBoost and others. We use also benchmarks to see the added value of machine learning and TAB-PFN, and these are quite simple models do not, okay, peak FFR can capture the seasonal variability, but this null model and trend model are capturing only, the trend model is capturing the trend, but the null is really a simple model, average observed yield per unit. This is quickly the workflow. For example, in the first plot, you see the machine learning based work. So for each of the feature sets, we do additional input features. So for example, yield trend and one-hot encoding. Then for each of these, we do the PCA or minimum redundancy, maximum relevance. And then for each of the models, we tune in a leave 1 year out cross-validation the model. So leave 1 year out is when you leave, for example, year 2002 to get the performance metrics for the model trained on the remaining years. And this is a typical approach in time series for crop yield forecasting. Tab PFN in the default mode does not use this double loop. It's only using one test year because it's not tuning, it's just zero shot. And then the post hoc ensemble below is using also this double loop, and the tuning time is a bit longer, but still it's quite fast. And this already shows the simplicity of the Tab PFN approach. And these are the results in terms of the relative root mean square error in prediction. So this is results in hint casting. So we got by leaving 1 year out for all the crops, we got this performance. Relative means that the root mean square error was divided by the mean value of the yield per crop. And we were a bit shocked with these results because in only 20 seconds, the Tab PFN almost had the same performance as the best machine learning model. The best machine learning model for maize, for example, is GPR, and it's using, you see the main features that it's using, the yield trend, the one-hot encoding, PCA, and the relative root mean square error is around 7.4%. And the letters above the bars are come from the ANOVA statistics and Tukey compact lecture display. So it means that, for example, letter A, the machine learning model, and Tab PFN belong to letter A. There are no significant differences between the root mean square error for these groups. While group B and C, which is null model and peak FFR, are different than this group. However, trend model for maize belongs to group A and C, meaning that it shares similarities with machine learning models. So, because for maize there is a high trend value, and for soybeans it's a similar case. The Tab the machine learning model, the best machine learning model was support vector regression. It was a bit better than Tab PFN. And for sunflower, it does not work, so none of the models managed to beat, when it's checking the statistical significance, was not able to beat the benchmarks. These are also, the Tab PFN also has a module for sharp feature importance. You can see also that for maize, the trend was the most important feature, also for the machine learning models. Then FP max M5 means it's a FFR maximum from month 5. And then you have other important features. For soybeans, it's different. Using the categorical variable admin name is the most important. Then you have the radiation, and then trend also here. And then other features. We did the operational forecast for 2024 for maize by using the best machine learning model and the Tab PFN. In light blue, you have this is F yield. It's actually the machine learning model. And you can see that across the regions, both machine learning and Tab PFN were able to capture the variable yield. And comparing to the official crop estimates committee in green forecasts, they're aligning quite well. Only in Northwest, there are a bit bigger differences, but the approach is giving quite good results. So these are the conclusions. Tune and sample did not improve the predictions. Kernel-based models were also better than the decision trees. For sunflower, it doesn't work. Maybe it's due to the crop mask also. We need to expand the analysis to several countries, and also maybe to see why the tuning is not working properly. And yes, also some other activities quickly. We are working in several countries for subnational forecasts. Also, we work at national level with University of Valencia and FAO JUICE. We will have soon a meeting with them and to announce the second version workflow. We also collaborate with NASA Harvest and FuseNet. We have regular meetings and sharing our forecasts because many institutions are now doing the same work. So we are building consensus. So if one of us is having really drastic differences, then we are talking about this and seeing what is happening with the data or with the models. And then there will be a new data set, crop statistics data set for Middle East and North Africa, published by GRC together with FuseNet and Harvestat. This may be towards the end of this year. And the Harvestat Consortium is also this organization that is gathering all the institutions interested at working at subnational level for crop yield forecasting. And yeah, so this is it. Thank you for the attention.
I apologize that I didn't introduce you. I'm sorry, but you started well. So, any quick questions? We're almost at time, but does someone have a question? There's one in the back, middle.
Hi, thank you. Could you expand how to use the MODIS data? So, do you just like rasterize it, or you pre-compute the NDVI or something and then rasterize it, or just?
So we use the MODIS data we have a raster, so and then okay, it takes some time. We use a crop mask, and we spatially average for the crop mask. We spatially aggregate the MODIS data, so for each year, and then for each month. So it's a decadal data. So then for each month we aggregate this.
So you do not convert it to a vector, let's say. You just get one value. Per province, we get one value per date. For every 10 days, we have one value. Okay, thank you.
Okay, I think in the interest of time, we'll move on, but thank you again. Do we have our second speaker? Yes, okay. And our second speaker is Dr. Loredano Spezzi from UMITSET.
UMITSET, yes.
Yes, take it away. Thank you.
Thank you very much. So my name is Loredana. I'm a remote sensing scientist working at UMITSET. And today I'm going to give you an overview of the machine learning approach that we are using at UMITSET for the retrieval of operational cloud products, specifically for cloud masking product. I have to stress this is a cross-organizational work which involves many people listed here, some of them working at UMITSET and others working in a company providing service for UMITSET, specifically in this case LOA and Brockman Consult. So I'm going to give you a very brief introduction of the UMITSET mission and specifically the operational cloud parameters cloud product that we retrieved at UMITSET. Then I will present you the traditional and current approach that we have for cloud masking at UMITSET, highlighting the limitation, and finally, the way we think machine learning and including the foundation model can actually help overcoming this limitation. So in this picture, you have basically a timeline of the satellite operated at UMITSET in the last decades, including the satellites that are going to be launched in the next 2 years, like EPSSG or the CO2M mission. And this satellite developed in collaboration with ESA and the Copernicus program. But what is common to all these satellites from the UMITSET point of view is that they have to provide operational product, and the operational product have 4 specific requirements. The first one is that they have to be reliable 24/7, so no missing data, no outage of data. The second one is that they have to be produced and disseminated within 10 to 20 minutes of acquisition, so depending on the mission, so very, very fastly. Then we have, of course, the requirement of quality in terms of precision, accuracy, and so on. And the final requirement or consistency over time, meaning that the quality of this product has to be maintained over decades for the entire mission lifetime, but also across mission. This set of requirements is very important because if they are not respected, the user cannot actually use this product for their application, which basically spans from numerical weather prediction to aviation, nowcasting, and climate monitoring. This is important when we think about introducing machine learning in these algorithms. So this is just a table of the variety of cloud products that we retrieve at EUMETSAT, starting from the basic cloud masking, which is also an input to many other retrieval, and then continuing with cloud opide, albedo, type, content of liquid and ice, water, and then, of course, related parameters like the total water vapor content and the aerosol properties. What you see here in green are products that are already operational. In blue are the products from the future satellite or product that are under development, and in red are those products which are under consideration because including, for example, machine learning approach or including the foundation model. So now briefly, how do we retrieve cloud masking? So the traditional approach at EUMETSAT is a spectral-based approach, so it's a direct computation of the cloud masking starting from the spectral information coming normally from imaging sensor with very high resolution, which varies between a few hundred meters to a couple of kilometers, depending on the sensor, and in the spectral range between 4 and 13 microns. So different type of clouds emit or reflect light differently depending on the channel. So we perform the so-called detection test in each channel, specifying specific threshold above which we expect the radiance of the cloud. Then we combine all these detection tests using the traditional decision tree method. And finally, we get the cloud mask. And to each pixel, we also assign a cloud probability using traditional statistical method as, for example, the bias theorem. Same for the other cloud product. For the other cloud product, we have normally an iterative minimization, which is known as optimal estimation or 1D-VAR, where you compare the satellite radiances with the prediction of a radiative transfer model, which assumes a certain set of cloud parameters. And then the process minimizes the difference between the two until it finds the solution in the cloud parameter space, which gives the best representation of the measurement. And this is how a cloud product appears at the end. So you have the cloud masking here that you can see. I mean, this is an RGB actually. And then you have the cloud height and the cloud optical thickness, and blue and green are the phase, liquid and ice. So same approach is used for other EUMETSAT retrieval, like the total column water vapor or the aerosol retrieval. And the limitation of all this that we encounter every time when we deal with more and more complex images with more channel, higher spatial resolution are basically these. The first one is the timeliness, because as you know, radiative transfer simulation are very time consuming. And the more channel and the higher resolution you have, the more time you need. So normally for new satellites, we cannot perform radiative transfer simulation on the spot, but we have to rely on lookup table at the cost of the accuracy of the product, which is another of our requirements. So we have to find a compromise. Then radiative transfer requires a number of auxiliary information from the surface, from the forecast, and if this information is missing, you cannot retrieve the product, so you have a missing product, which violates another of our requirements. Then we have some critical scenes, for example, aerosol mixed with cloud or cloud above a very bright surface, where the traditional method not always manage to detect the clouds, because they are misinterpreted other target. And then we have that we are not using so far the temporal information, the subsequent information coming, from example, from geostationary satellite, which provide an image every 10 to 15 minutes. So we think we can address all this using machine learning technique, but I have to stress one important point. Use of machine learning technique in EUMETSAT operational product is expected to complement the traditional method, to improve on it, not completely to replace it. And the reason for that is one of our requirements is consistency over time, which is fundamental for climate studies, climate monitoring, and so on. So we cannot jump from one algorithm to the other, creating a discontinuity in the time series. So now some example of what we are doing to explore machine learning possibilities. So I will start with a very early work that we did actually recently using the foundation model. This work was done by Boran Frank, and which is unfortunately is not here today. So basically, in this very first test, we try to assess whether the foundation model can retrieve a cloud mask for the Sentinel-3 sensor, performing as well as or better than the traditional method that we use so far, which are spectral based, and in some cases also helped by other AI model. So the basic question is this: we use the PRITV from the foundation model for Earth observation. And as you know, this model is mainly trained on Sentinel-2 data and Landsat data. So it's mainly trained over land, not over ocean, and with a spatial resolution which is of the order of 30 meters, while for Sentinel-3 we have a resolution of 500 meters. So the early question that we answered with this very first phase of the study was, can the foundation model, PRITV-AO in this case, reproduce the Sentinel-3 cloud masking, recognizing the cloud paths, although educated and trained with Sentinel-2 data? The answer is yes. Here you have the result of our test. So we basically fine-tuned the PRITV observation model using a sample of 437 labeled training samples. And then we ran several experiments, some of them using the foundation model and other without the foundation model. And this is how the Jacquard index, which is basically a quality index on how well your model reproduces the labeled sample. So when we do experiment using the foundation model, we are here. So the index is about 0.85. When using the traditional neural network that we were exploring before to improve the masking, we are about 0.75. So the PRITV foundation model basically provide a 5-6% improvement into the cloud masking. So the answer is yes. Landsat is, although the model is trained on Sentinel-2 and Landsat, it's still useful for Sentinel-3. And this is an example of the masking. This is the traditional mask, which is a pixel by pixel mask. So here you have a very, very high resolution, which is the native resolution of Sentinel-3. And here, for the same scene, you have the result of the PRITV foundation model, the prediction, which, of course, is muted, as you can see, but fully reconstruct the cloud path. So this is a path that we are exploring, not yet finished, actually at the very beginning. And I thank again Boran for this work that he did for us. Then going on, we have also had a method that we are exploring to improve cloud detection. One of them is the optical flow. So it's a computer vision technique which basically analyzes structure in subsequent images. And this will allow us for the first time to actually use in our operational product also the temporal information, the cloud evolution. So in this case, we basically use the optical flow to construct the optical flow vector for each object that we have identified in the image, and then we establish threshold for the motion that we expect for clouds. And we end up solving some of our critical cases, those cases that I mentioned that where cloud detection is really tricky because maybe you are mixed with aerosol or you have a bright surface below. So here I show you just two cases. So this is a smoke plume over the Sahara, and this is the Red Sea. In the traditional cloud mask, both of them are classified as cloud because spectrally they are as bright as clouds. When you use the optical flow, so when you actually analyze the movement of the clouds, then you have that both of the features are disappearing from the mask, mainly because their motion is not consistent with what the optical flow predicts for clouds, because the Red Sea is not moving, obviously, and even the Sahara dust plumes moves differently than cloud. So this is also very promising. Another example here we use differential evolution technique to basically optimize the threshold in traditional cloud spectral test. Basically, the differential evolution optimize the full set of threshold of each cloud test in its channel in the whole hyperparameter space defined by the threshold of each test. This is something that with the traditional decision tree you cannot do. So, and by applying this method to several cases, we find out that in some cases the results are unchanged, so same as our traditional mask, but in some cases are improved by 1 to 10%. So very, very good results. Still going. And finally, I leave you with a very, very quick list of other projects that we have related to machine learning. In this case, we are using deep convolutional neural network to simulate visible channel at night. As you can see, the reconstruction is very similar to the truth. The reason for this is that optical properties of cloud, such as optical thickness, particle radius, they are better retrieved during day thanks to the visible channel. At night, we don't have the visible channel, so if we can use the machine learning prediction, assuming that the cloud maintains the same properties at night, then we can achieve a better retrieval also during nighttime. Then we have a project related to aerosol. In this case, the neural network is a TensorFlow, and the neural network is used to speed up the forward modeling, basically to speed up the radiation transfer to simulation and the computation of the Jacobian that we use in our optimal estimation. Then we have another project using XGBoost to speed up the CLIM cloud mask. CLIM is the imager of the coming CO2 mission. In this case, the neural network is also used not only to speed up the processing, but also because XGBoost, apparently, because we are exploring this, has the capability of learning about the inputs. So over time, the machine learning gives you also a climatology of the input auxiliary data that you can use instead of the real auxiliary information in case this auxiliary information, like forecast or surface property, are not available. And this helps us in the reliability of our products, which, as I mentioned, they have to be available 24/7 with no missing data. And finally, a project which we just started within the destination Earth application demonstrator. In this specific project, we are using deep learning technique, which is actually performed by a contract for EUMETSAT. We are using deep learning technique to merge cloud product from the geostationary SEVIRI and FCI imager with the destination Earth weather-induced extreme digital twin, hoping that this way we can improve the quality of the short-term forecast for clouds. And with this, I thank you for your attention, and I welcome any question or suggestion.
How about we do one question? Who's got the great question? No pressure. Others? Okay.
Hello, thank you for your presentation. Can you elaborate more on how you plan to integrate the cloud mask derived by the foundation model with the existing pipeline without replace it?
Yeah. We actually didn't think so much about it because in the other cases that I show, like the deep learning enhancing the decision tree, it would be simply an addition of one step which completes the detection test, the traditional one. In the case of the foundation model, this is not possible. So the only way I see at the moment is that for a certain period of time, we have to run the two algorithms in parallel, making sure that they produce the same results or even better in the case of the foundation model, or same or better result over a long period, meaning over all the scenarios and that we have. So all season, all kind of land and sea surface and so on. So this at the moment is the only way that I foresee, because unlike the other method, the foundation model cannot be merged in any way with the spectral test that we perform ahead.
Okay, thank you.
Thank you.
Thank you very much. Okay.
Now, next speaker, Ferdinand Skank, please. Thank you.
All right. Hi. Yeah, so hi, my name is Ferdinand Schenk. I work for a company called DAY2, and I'm going to talk to you today a little bit about how we are using foundation models for very high resolution bitemporal change detection. So just a quick note about DAY2. We're a company that was established in 2018 in Berlin. We have offices in Germany, the UK, the US, and Latvia, and we employ about 120 people from about 30 different countries. And we have customers from all over the globe. DAY2 has three main products: Treeline, which is satellite-based vegetation monitoring for line infrastructure, so power lines, railway lines, that kind of thing. Surface Scout, which is the automated detection of third-party interference along pipelines, and TradeAware, which is deforestation detection and compliance management, mostly in the context of the EUDR, which is coming into effect at the end of the year. Today's talk is mostly going to be focused on some work we did around Surface Scout, which is automated detection of third-party activity along pipelines. What does this mean? So the business problem that we're facing here is that gas and oil pipelines are vulnerable to human or natural activities, such as construction, farming activities, or erosion. And if you look at this report from the European Gas Incident Group, you can see that for the majority of holes that are formed in gas pipelines, it's mostly due to external interference, which mostly means someone digging a hole where they were not supposed to be digging a hole because they didn't get planning permission or because they just didn't think it was worth it. And otherwise, it's ground movement, which might be due to erosion or flooding or something like that. So yeah, pipeline operators are required to perform regular inspections along their pipelines. Depending on which country they're in, this might depend a little bit on the frequency they have to do this at. And yeah, we're trying to help them solve this problem. So the technical problem, we've effectively phrased this as a bitemporal change detection problem. Basically, we get a satellite image every 2 weeks to 2 months. And effectively, like all change detection problems, it's not really about detecting visual changes, but distinguishing between relevant and non-relevant changes. So relevant for us in this use case are construction and ground movement for whatever reason, and irrelevant are things like changes in shadows or changes due to different imaging angles for different satellites or seasonal changes. You can see this is an example of 2 images from our data set of the same location, but one was clearly taken at a case where the sun was right overhead, and the other one was taken later or earlier in the day when there are long shadows and the image is significantly darker. These are irrelevant changes to us. To give you another example of non-relevant changes, this is taken from Sachi's paper, and you can see here the trees have lost their leaves in the top image. Again, irrelevant change to us. We don't care if trees change leaves. And again, shadows are irrelevant to us in this use case, and so is the movement of cars as an example. So the data problem. So we need a couple of things to actually deliver to this product. The things we need is we need a relatively high revisit rate because we need to be able to get images at a relatively short timeline. We need sub-meter ground sampling distance because we need to be able to detect relatively small changes like someone digging a ditch. And the data also needs to be available at a reasonable cost because above a certain price, it just doesn't make financial sense for us to offer this product, which is usually the case in commercial Earth observation. So the only constellation which at the moment really fulfills all of these criteria for us is the Planet SkySat constellation, which currently has about 15 satellites in operation. They used to have more, but they deorbited some of them recently. So yeah, even though it's one of the more reasonably priced, very high resolution satellites. It's still quite expensive, with between hundreds, maybe low thousands of euros per image. And you know, the usual thing to do in a case like where we do get data is we do actually get data when we're doing the work for our customer. Is usually you would say like, hey, why don't you just label the image that you get for your customer? And that makes sense, and we do try and do that, but quite often in, for example, like 2 weeks, not much has changed. So you might only get like one relevant change per image, which means you're effectively paying several hundred euros for a single label, which doesn't really make sense. It's also restricted then to the geographies of your current customers, and these models might not you know, work on as well as on new customers in different geographies. So how do we plan on overcoming these issues? So luckily, because we buy quite a lot of data from Planet, they've allowed us access to the SkySat archive and to a limited extent. So we're basically searching through the SkySat archive for data that are more than we are still looking for pairs that are more than 365 days apart. This makes sense. In a year, a lot might have happened. So the further apart the images are, the more has happened and the more likely you are to have a change in these images. We're looking for images near human activity. You know, you can take images in the desert and even over years, not much might have changed, whereas near cities, things change because, you know, people do things. And yeah, we want to sample these images across different geographies because we want to be able to deliver our product to customers in different areas of the world with very different biomes. So if you look at this, we managed to find, this is just a heat map of some images. Oh, it's a bit washed out here, but we've managed to find quite a large amount of data there that we could actually download, and we had to like subsample this a little bit and select data that we could actually use. So going on to the labeling strategy, so labeling is the next big thing. We want to be able to label, need labeled data that where the changes have been labeled. This is one example of a labeled image that we have that our wonderful annotators have annotated for us. As you can see, someone started moving some ground around here, and usually when people start moving earth and there are earthworks, it's usually a sign that some construction is going to begin. And so this has been labeled as a change in this case, and this is exemplary of the kind of changes that we are trying to find. Currently, at the moment, we have 6 labeled SkySat scenes, which is, you know, a little bit less than I would have wanted, but that's what was available at the time I had to start doing the work for this workshop. In this case, we're using 5 of them for training and 1 of them for testing. We got about 6,000 labeled change polygons, which, when we chipped this into images, turned out to be about 1,600 labeled 512 by 512 pixel pairs. So why are we interested in foundation models? As you can see by the amount of labels we have, we work in quite a limited label domain. We also have lots of different types of changes, some of which might be quite rare. So we really want a big model that can really like reason about like what a relevant change is. We also need a model that can generalize across large variations in biome, solar angles, view angles, seasonal variations, and land use patterns. If you think about it, like a model that's trained on only 5 images has only seen 5 variations in solar angle and 5 variations in view angles. And we really want a model like this to be able to like not be robust against changes of solar angle and view angle and all kinds of things that usually come with remote sensing images. So we set up a quick foundation model test. We needed to answer a few questions. Do we really need foundation models, or will smaller models suffice? Can we use general purpose foundation models, or are geospatial foundation models better? Does the ground sampling distance of the data that the foundation model is trained on matter, or is that irrelevant? And how big is big enough for our use case? And the last question, because we're only using foundation models that other people have trained so far, we want to answer the question, do we need to train our own foundation model, or can we use one just off the shelf? Of course, if we don't have to go through the hassle of training our own foundation model, we would rather not do that and rather just use something that someone else has created. So how the test was set up is we have a little baseline, which was just change former with MIT-B1 backgrounds, a nice little small model that we've been using just for prototyping, just because it's small and quick to train and gives you pretty good feedback pretty quickly about like how good your data is looking. And then for the main test, we basically set up a bunch of 100 million parameter models. We wanted to keep this fair, so we didn't want to compare like apples to oranges, so we wanted to keep a specific size, and there were quite a lot of foundation models at this 100 million parameter model size. And then we have one bigger model just to see if size really makes a difference here. Our challengers here are DINO v2 with the original natural image weights from Meta, Then the exact same architecture, DINOv2, but with trained on the SAM-RS dataset, which has a lot of remote sensing images, including aerial images and some satellite imagery. Clay v1, which I think most of you might know, Prithvi v1, most of you might know. Both of these are 100 million parameter models, roughly, as well as base vision transformer, where some people did some nice things too. This model is from a paper called MTP, Advanced Remote Sensing Foundation Models, via multitask pre-training, where they've applied multitask pre-training to a model. And yeah, without much further ado, some results. There are some interesting results here. Prithvi did pretty badly. I don't know if this is just because I was using Prithvi wrong, but also Prithvi was trained on Sentinel-2 images, which are pretty far away from the sub-meter SkySat images that we're using. The vision transformer trained from scratch, i.e. with randomly elisionized weights, also performed pretty badly. No big surprise there, but this does tell us that, like, a pre-trained model is a good idea. The DINOv2 trained on natural images also didn't perform very well, but a little bit better. And yeah, then changeformer or baseline. Clay came in a little bit better. Clay was at least trained on some aerial imagery. I believe it was trained on the NIIP dataset. DINOv2 with the remote sensing images is where we start seeing models that perform really quite well. So yeah, that was the first big surprise. It's exactly the same model architecture as the other Dino case, it's just different weights, and it performs a lot better. The vision transformer trained with them as a masked autoencoder on, again, some remote sensing images, much better. And then the next big step up basically comes when you start using this model that was trained with multitask pre-training. This has to be said, one of the multitask pre-training tasks was change detection, so maybe it's not such a big surprise that when we then downstream fine-tune this on change detection, this is a model that's already learned how to do a little bit of change detection, or at least give embeddings that work well for change detection, I should probably say. And then, yeah, the last step, we basically took the best performing model, and luckily the authors of this paper had provided a bigger version of it, the VIT-L size of it, and yeah, therefore we used the large version of it, and as you can see, as we jump up to 600 million parameters, 300 million parameters, suddenly the model does quite a bit better, which is good to see. So a few takeaways: foundation models help. Remote sensing images matter. It's good to use a remote sensing foundation model. The ground sampling distance seems to matter because it seems that the aerial trained models are much closer to the very high resolution, sub-meter resolution satellite imagery than, for example, Sentinel-2 is, also spectral bands wise. Bigger seems to be better, like this is to be expected, but it's good that this is validated here. And multitask pre-training seems to help. So if you're training a foundation model, maybe consider that. Things we still need to clarify is, like, should we go even bigger? Is it worth it for us to go to maybe like the VIT-Huge or maybe Prithvi 600? And should we train a SkySat foundation model? I'm not sure what the answer is to this one. I don't know how to answer this without actually training a SkySat foundation model. If you have any opinions on this, please let me know. If you have trained a SkySat foundation model, also please let me know. I don't think anyone has, as far as I know. And yeah, future work, just a quick note on this. This isn't something we've started with this a little bit. We also have access to the Capella archive. So what we're actually doing is not just creating pairs of SkySat images, we're creating pairs of SkySat images and pairing them with Capella images for the same time. And because it's quite hard to label SAR images, we're using the labels from the SkySat images and using that on the SAR images. And yeah, we're trying to train then our optical-to-optical foundation model, which we're using at the moment, or sorry, optical-to-optical change detection model, which we're using at the moment. Later we'll do SAR-to-SAR, and hopefully even later cross-modally optical-to-SAR, so we can also serve clients in areas where it's a little bit more cloudy. But yeah, hopefully we've only really started on this, so hopefully if there's another version of this next year, I can talk to you about that. And yeah, some references if you are interested in the papers or sometimes just GitHub repositories of the things that we've used here. And yeah, thank you very much. I did this work in collaboration with two of my coworkers, Paul Weinmann and Martin Schickler. And if you have any questions or want to tell me that I used your foundation model wrong or that I should please use your foundation model, then yeah, please come talk to me. Yeah, thanks.
Thank you. Do you have any questions? We have time for a couple, maybe quick. Don't be shy.
Sorry, I might have missed that, but what are the foundation models that, like, where did you get them from? All these, like, in the bottom, like the VTV class?
So all of these last ones are actually just effectively an ablation study that I did on the foundation model from this multitask pre-training paper. So they're all just effectively, because I just used the normal one they had, which is multitask pre-training plus this rotated varied scale attention thing. And then with these different variations, I basically just did a little ablation study to make sure like which part of the work they did was actually the important part. Because they add the rotated varied scale attention, which is just their new variation on varied scale attention. But I wasn't sure if it was the multitask pre-training doing better or the varied scale attention, and then I did an ablation study, and it turns out to be the multitask pre-training and not so much the rotated varied scale attention. Yeah, sorry, should have explained that better.
Cool, thank you very much.
Sure.
So when you convert the labels from optical to SAR, do you use any corrections for things like buildings and so on, which I guess are probably projected differently?
Like I said, we've basically in the data collection phase of that project. That's future work, like I said. So ask me next year and I'll probably be able to answer that question for you.
If you have time for one more online question, so S.Sobul from JAXA is asking for pipeline monitoring. Is it also useful to use cluster deformation, and do you plan to use INSAR as part of your foundation model?
Ooh, no, I mean, INSAR is quite interesting in there because one of the big differences, one of the big problems that these operators often face is ground subsidence. And like INSAR is really great at like seeing over a long period of time, like if ground is like sinking or raising or stuff like that, which is often what like then bends and breaks your gas pipeline. But as part of this product, we're not using that. But it is, I mean, it's a very cool approach, but it's also just like a very different modality and a very different way of solving a problem.
Perfect, thank you. Once more. Now we call the next speaker, Mauro Silos Labini, please.
So, hello everyone, thank you. There is a little shift because my name is Nicolò Taggio, but it's a colleague of mine, Mauro, so it's okay, don't worry. I want to say thank you to everyone, to your community for this conference. It was very interesting, is very interesting, and this is the future of Earth observation domain. My name is Nicolò Taggio. I'm going to explain you fine-tuning PRITV on large-scale land cover segmentation task as a joint work with the Planetech Italia and the Planetech LAS. Planetech is a space company, and we are able to cover, let's say, the entire chain of space from the downstream to software on board. So we have more than 31 years of experience. So I'm proud to be here to show you our experience in this problem. Before to start, I want to just give you an overview of the problem. So the problem that I'm going to show you is just a land cover classification. Okay? It's a very, very simple problem to explain, not to solve it. And I want to answer during this presentation different questions. First of all, typically in our work, maps are generated by human. Okay? And we want to understand if it is possible to help the human effort. Also, we want to assist them to accelerate their work. And finally, we want to understand if it is possible to use a geospatial foundation model instead of a standard segmentation algorithms. So let's start with the use case description. As you probably know, population in the world, more or less, lives close to coastal area, okay? And in particular, Europe citizen lives, the 40% of the population lives across not, but close to coastal area. So this is the problem. We want to understand what happened in the coastal area because we live there, more or less. And the European Environment Agency play a key role because they provide a product each 6 years to update the land cover in the coastal area in Europe. Land cover means, of course, we want to understand if there is some vegetation or urban area or other kind of land use, land cover. And in 2018, Planetech led a very, very big consortium with GeoVille, Telespazio, and Planetech LAS to map manually the entire coastal area in Europe. So This means 71 different land use land cover classes that are very, very similar to each other. I want to explain you better what I mean. And we collected a lot of satellite data in 2012 and 2018. So now starts the idea why we need to use deep learning. First of all, because we are more or less in the, let's say, perfect storm, because we have data that we manually extracted. We have an expert, because we manually extracted the data. And we have data. So this is a perfect storm to machine learning approaches. But not only, because the entire process was done manually. So can deep learning help us in help this approach? And we spent a lot of human effort. So more than 30 people works for mapping, for segment manually all this land cover land use. And many different multi-data sources were used. So deep learning can help us in generalization. Also, as I mentioned before, 71 different classes is used. We want to better understand how to distinguish very similar classes. And last but not the least, we used commercial data. This means for a private company, a cost. So we need to reduce cost, and we need to try to understand if it's possible to substitute something that is a commercial data to something that is free data. So, and that's why we tried Prithvi, a foundation model that works with Sentinel data. Now, everyone know better, maybe I'm sure better than me what Prithvi is. And, but the idea that I want to highlight is that Prithvi was one of the first geospatial foundation model based not only in the standard, let's say, RGB plus near bands, but only with also SWIR 1 and SWIR 2 bands. So this is the idea why we used Prithvi 1.0 EO. I want to explain you our feasibility study. Okay, so first of all, what we did the data collection. So we collected everything that we used during the past project. I mean, Pleiad, SuperView, Spot, PlanScope, and Sentinel. So we prepared every data for our task. And this is just a summary of differences between data. So differences are in resolutions, for example, because we have 2 meters, 4 meters, and 10 meters. We have also differences in digital code, because we have something that is a 60-bit, 11-bit, 12-bit. So we need a very huge normalization of this data to work with all this data. And this is an overview of our ground truth. So 71 different classes. This is our 5 levels. Actually, in this feasibility study, I will show you our results in the second levels. Let's say only 26 different classes. Sorry for the resolution of this image, but I think it's okay. So what is our area for the feasibility study? We selected 2 nations to start our study, Albania and Ireland. So why? Because for 2 reasons. The first reason is that we want to demonstrate the scalability of our framework, because we want to pass from 3 GB to 30 GB, so a scale up of 10 times. And the second reason is that because we have a very, very, very unbalanced ground truth data. And using these 2 nations, we limit this unbalanced. But as you can see in this slide, we continue to have a lot of unbalanced distribution. For example, in the level 1, in left side, the orange one, grassland, contains 40% of representation in our nations. And if you see level 2, in the green boxes, 52, alpine scrubland, we have 0.00094% of presence. So this is the reality. So this is what a private company needs to do. So ingest different data and work with unbalanced ground truth. So let's start with some results. This slide shows you one of the main problem that we have in this study. is that the ground truth data has a 0.5 hectares of spatial resolution, while, as you know, Sentinel has a 0.01 hectares of spatial resolution. The other satellite data has more 0.0004 hectares. So this means that when we try to train some automatic algorithms, the error can be affected of this different resolution. We build a big workflow that is able to prepare data using our dataset builder, a training step to fine-tuning a lot of hyperparameter, and also a validation step. And just to give you an idea, using a Prithvi, for example, if we have in the future, and I hope so, a training of the entire Europe, to perform a prediction of the entire Europe, we just need 2 days with a let's say, standard GPU. So it's a very, very quick process. What about the quantitative results? So what we did is compare the level 1 and level 2 overall accuracy. When we use Prithvi and UNet using Sentinel-2, Prithvi performed better than UNet. When in the level 1, when we use the very high resolution data in UNet, UNet can perform better than Prithvi. But this is the most important information for our company. When we pass in level 2, Prithvi perform similar to UNet. What does it mean? It means that we can save money because we can use free data, Sentinel-2, instead of a lot of commercial data to perform the same task. Okay, this is let's say, the message. The message is that we can use freely data instead of a commercial one. While these are some qualitative results, and as you probably know better than me, UNet performs some blobs instead of Prithvi that is more accurate. And you can see also the differences in spatial resolution, because the ground truth data, I want to remember that it's 0.5 hectares. To give more detail about qualitative results, I want to show you a slide with a GIF that represent a vectorization of a big area in Ireland. And for what is our, let's say, meeting with the EU expert in Planetech, this is that this is very useful to go faster in the segmentation. And this is the level 1. So this is the same example of level 2. So without any post-processing, because of course we are GIS expert also, so we can improve these results that are automatic generated by Prithvi. We can improve the results of this segmentation. So take home message. What we did is developing an entire pipeline able to perform classification using data, satellite data, whatever you want. We compared freely available satellite imagery with the commercial one, and we can say, we hope on that, we can replace commercial imagery with the freely one. And accuracy may vary depending on spatial resolution, so we can improve our result studying better the ground truth data, and also to extract validation points from our expert, not polygon, but points. And last but not least, we can provide faster and higher resolution updates, because EA Coastal Zone provides this product each 6 years. Okay, with this method, we can say, I don't know, each 3 years. So, but we can go faster, and also the resolution we can pass from 0.5 at least at 0.1, not 0.01, but we can say 0.1. And what the next step is that, of course, this framework is able now to ingest all the geospatial foundation model. And thanks to this conference, we have many ideas about all the geospatial foundation model. And I'm so happy on that. And another experience that I want to explain to everybody is that maybe one model cannot be able to perform everything. Okay, we can pass from one model to a sort of hierarchical model, so something that is data-based or I don't know, ground truth-based. So we know that one model can be better than for urban classes. Another model can be better with a vegetation class and something like this. And last but not the least, by the end of the year, we aim to generate the first fully automatic European coastal map at level 3. So thank you very much for your attention.
Thank you. We'll have time for some questions. One there. Okay, perfect.
Hi, thanks a lot for the talk. I was just wondering, do you expect you can apply this model also everywhere, so not just on the coastlines, and produce, you know, a land cover map for the whole of Europe at this level 3?
Yes, thank you for your question. Of course, yes. So this model is not related to the coastal area, so it's related to images. This means that we can perform land cover and use in the entire Europe. So it is not planned yet, but thank you for for your suggestion, because of course we are able to collect Sentinel-2 data, of course, with let's say effort 0 for different reasons. So we will take your message and thanks. For level 3, we will pass from 26 to 45 different classes. So it is quite difficult to pass to all Europe because the photo expert maybe can help us in modification of the final product. It's not something that is user ready with only AI, but we need, fortunately for everybody, human effort.
Thank you. Any more questions?
So we do have an online question by LB asking, how do you intend tackling the hierarchical aspect of the model? A different model per level of classification, or rather a single model for all levels at once?
Okay, thank you for your question. Yes, actually this hierarchical approach is an idea that we study in the state of the art, because in another context, for example, in habitat mapping, we study, thanks to Vito company, that they performed a very deeper classification approach with a hierarchical one. So this means that we need, first of all, a model for level 1. And then inside, I don't know, urban, that is class 1 of the level 1, we can perform another model only to the classes inside the urban area, and so on. This model, of course, can help in accuracy and can help also the photo expert that we have to segment only small part of the model.
Thanks a lot.
Thank you.
Okay, thank you. So we move to the next speaker. So María José Martínez from DAY2, please.
So good afternoon, everyone, and thank you for being here today. My name is María José Martínez, and I work for a Spanish company that is called Indra, and I am part of the computer vision and artificial intelligence team. So today I'm going to be talking about part of our project that is called ESA-ESRIN. And so this is a quick overview of the project and all the content that I'll be covering today. So let me start off by introducing ESA-ESRIN as an innovative Earth observation mission that detects, performs early detection and also rapid response for disasters like wildfires, floods, landslides, and other non-related disaster use cases like ship detection. So yeah, this is a quick video for you just to have a more complete view.
Natural disasters are becoming increasingly frequent. Detecting them early and responding quickly is key to saving lives. We present ESA-ESRIN, an innovative solution designed to support emergency and security forces. ESA-ESRIN is built on a real-time satellite data processing service, providing Earth observation tailored to critical situations. It is a project co-funded by ESA's Civil Security from Space program and developed by Indra Deimos, GINA, and Skylabs. How does ESA-ESRIN work? The satellite orbits continuously, performing early detection and prediction tasks. While in orbit, it can receive a request to observe a specific area of interest. Using the Retasker module, the satellite checks if it can perform the necessary maneuvers to reach the area of interest. If feasible, the satellite's trajectory is adjusted to include the requested area. Once positioned, it receives instructions and captures the required images. These images are processed on board using AI to identify damage and risks. Alerts and Earth observation products are generated and transmitted to the operations center. The information is transformed into maps and data layers on the platform. Finally, emergency teams access the data through an app to act quickly and effectively. Thanks to CISRI's Earth observation mission, we will be able to reduce disaster-related deaths and damages by up to 30% and accelerate emergency response by up to 80%.
So one of the first challenges that we faced in CISRIS was the early detection of landslides. This is because, well, first of all, just for you to know that it's a very major problem worldwide because normally it causes up to 70,000 fatalities each year and also affect up to 15 million people worldwide. So the first thing that we had to do is to collect some data. This is the pipeline that we designed for the model training and inference. So what we discovered is that the majority of data sets, they didn't have the geolocation data that is crucial for early detection because we need to cross the DIM data, that is the elevation data, with the normal satellite imageries. So the DIM is very important because we found that when you have a mountain or an elevation that is inclined, there is much more risk of producing a movement terrain rather than when you have the terrain just like a plateau, like plain. So yes, we came up with this solution to develop an algorithm that automatically geolocates these data sets. So it takes as an input the target image. So the target image is going to be the one that has no georeferencing metadata. That means that we cannot geolocate it in the map. So, and we actually need it with geolocation. So we have our target image and its corresponding ground truth. And then we have a reference image that it is actually geolocated. So once we have these inputs, we input the algorithm with it, and it generates the target image geolocated, and also performs a data augmentation part in which we reconstruct the original image, the target image, using the pixels from the reference one. So this is important because we have two findings, like we have geolocation algorithm and also data augmentation part. So just a brief, quick note of the state of the art. So basically, our proposed method, what it has as a novelty is that it is do both things, the data augmentation and the geolocation. So we tested our model with the CAS landslide dataset because it is a worldwide representative database, and also it has a lot of environments included. For example, we can see here the landslide occurring in a rural environment, also near an urban, also in mountainous terrains, near the coast. So we found it very good representative one. So this would be our target image, the one that is not georeferencing. You can see here in the column that we count on several sensors and sensor resolutions, and we use as a reference image just the Sentinel-2 with the typical 10-meter resolution. So this is the general pipeline. This is our step of collection data. So from the data, we get three inputs: the non-geolocated satellite image, which is annotation, and also the area of interest from which we are going to download the reference image that is geolocated. So the block, I've divided the block in three parts. The first one would be the feature matching. The second one, the part in which we reconstruct the image, so we do the data augmentation. And the last and most important part is the target image geolocation. So how we do perform feature matching? Feature matching is simply to find the same points in two images. So because of the reason that the reference image is so big, is massive, we have divided it into patches. So the algorithm, what it does is to select the best one based only on SIFT. This is a very known algorithm. So once we have SIFT, what we have done is to include a pre-trained deep learning model called LoftTier to enhance the matches from the patch, between the patch, that is the reference image, and the target image. So as you can see, normally SIFT has few matches, but very robust ones. That is why we use it alone for selecting the best patch. And then we use the LoftTier just to augment the matches. So the second part is the reconstruction image. So once we have our matches, what we do is to create an homography. That is a mathematical formula that we use to relate to spaces image, like it's more a computer vision part. So using this relationship between the two images, we can use the pixel information from the reference one and then reconstruct it like the target image with its information. So once we have our reconstruction, we need to add the geolocation itself. So we do it by using the geotransform that, for the ones that you don't know, is a matrix that has all the information about resolution, geolocation, and everything in satellite images. So we transfer the geotransform to the reconstruction, and then in this way, basically we get our target image reconstructed and geolocated. So where is the part that is happening the data augmentation? In here, because as we have already the task mask, the target image mask, we can also, using the homography, adapt it and then have our reconstruction and also the mask adapted to the reconstruction. And also our original target image geolocated. So we have the database usable because we have the metadata, the special metadata, and also we have more data from another different sensor, different resolution. So this is very interesting because we found that using, if you remember the path selection that we only use SIFT, I decided to, okay, let's see if we use both the SIFT LoftTier for the best selection path or just LoftTier. So maybe you can feel that we get similar results just for the fact that LoftTier is 6 times much less rapid than using SIFT plus LoftTier. But if we take a closer look, we will see that LoftTier alone is not gets a lot of more, a lot of less geolocated images itself. It needs after the reconstruction, it needs to apply a filter to the reconstruction to get these good results. So basically, what we have discovered is that SIFT is very robust algorithm, and the LoftTier is good for augmentation, but it's not for getting robust results. So here is to illustrate it. We have here our reference image, that is the one that is geolocated, and here our target image. So with SIFT, we get few results, but very robust results. But when we add LoftTier, very many times what you see is non-parallel lines, but these kind of lines that is saying that is not good results, good matches, because they are not actually good matches. So when we apply a filter consolidated like ransack, we just get 2 more points from LoftTier. The rest are coming from SIFT. So that is the main reason that we use SIFT for selecting the best path and not just LoftTier. And then this is the results. So as you can see, our algorithm is capable of geolocated 1 out of 3 part of the images. So this is very good results, taking into account that a lot of images have clouds, but illumination, a lot of homogeneous structures like vegetation, and also differences in time acquisition and luminescence and these things. So this is the very good part, like our good results. You can see here the target image, and for example, an example of its corresponding reconstruction that, remember, is fully built upon the pixels of the reference image. So we estimated also the geolocation error, and we got an error of less than 30 meters, something that is very good, but it depends on the target of the project. But for us, because we want to cross the data with DEMs, it's a very good resolution. And yes, so to identify these non-valid reconstructions, what we did was to select some similarity metrics, and we finally found that NCC is the best one to distinguish between invalid reconstruction and valid reconstructions. So with this, what we can do is massive. Like, we can get other data sets and get this estimated percentage of the images geolocated and hence usable for us. And also we can extend it, the use case, and use it for other detection, for wildfire detection or flood detection. So it's an algorithm that it can be applied for any use case. And also, just for you to know, inside the project, my colleagues are also developing another ways of data augmentation and data usability. So for me, the most important thing for you to know is that we have an algorithm that is functioning, that is capable of geolocate images that are not geolocated, which is something very important nowadays, because databases are normally, as you may know, just released with 3 bands, for example, a color composite composition, and also without all the data that we need, for example, the geolocation. And also, I would like you to know that even though SIFT is a very classical algorithm and method, it resulted to be better result, like to have more robustness and reliability comparing to more modern pre-trained models like Loftier. And yes, thank you so much and for your attention. If you have any question, please don't hesitate to reach out. Also, you have here the QR for CSIRO's mission if you are interested to know more about it. And here is my LinkedIn and just my contact, just in case you have any question or you want to collaborate or everything. And thank you so much.
Thank you. We have time for one short question. Well, it's a slightly different topic, let's say. Okay, if there's no question from the audience, I have a question. So how far are you from operational usage of the workflow? Because you now demonstrate with some images, you plan to extend to real use cases. What are the challenges that you could foresee?
The challenges? The challenges would be to expand this to other databases, because you have to take into account the different resolutions, the different sensors, the different characteristics of the images. So fortunately, with this dataset that has all these different characteristics, it is working. But it's true that we have to apply into other databases, as I mentioned, and other databases from other use cases. So nowadays, that's the main challenge that we are confronting, I would say.
Okay, thank you so much.
Thank you so much.
Our last speaker of today, there's a little change, so it will be presented by Mr. Asaro from Mind Earth.
Good afternoon. I wasn't expecting so many people to endure until the last presentation, so congratulations. I am Francesco Asaro. I'm the head of data at MindEarth. Sorry, where's the laser pointer? Ah, okay, they're separated. Well, today what I'm presenting are the results from an experiment that we designed together with my team that brings together 2 words, the one of mobility data and the one of remote sensing data, trying to answer a simple question: can we predict how people move simply using overhead imagery? you can imagine what could be the impact of having a positive answer to such a question. Half of the world population and counting is living in cities, so it's stressing its vital system, worsening the exposure of the population itself to hazards. And MindEarth itself works a lot in developing solutions and tools for enable informed decision for stakeholders. We developed the models of the City Nexus use case in Destiny. And so this really goes in the direction of our research and development. And the idea arose from the intuition that basically we could use a foundation model for extract meaningful features from aerial images and fed them to graph neural network that on the other end are the most natural architecture to treat mobility data. When I speak about mobility data, I mean something that in the sector is called high-frequency location-based data, most simply GPS pings. And so to realize this experiment, first of all, you need to create a discretized description of the geographical space. In order to do this, we use the H3 grid by Uber at resolution zoom 8. That is basically 0.7 square kilometer area. And once that we created this discrete grid, basically we had the underlying network to train the underlying graph to train the network on, where the nodes are represented by each H3 cell. And the edges are all the possible connection in the baseline cases between any of the H3 cells. What we did is, at this point then, to create an origin-destination matrix. That is a matrix that describes the probabilities of flows existing from one cell to all the others, and to create the vision embeddings from the orthophotos. The experiment was run on 3 cities, Copenhagen, Aarhus, and Odense in Denmark. And we used the public orthophoto from the Denmark Environmental Agency at 0.7, resampled at 0.7 meters, so 70 centimeters. And thanks to the grid and 1 year of empirical mobility data, we're then able to build the origin-destination matrix, which is our target in this task. This is an example of, in concrete, how an origin-destination matrix look. These are 2 separate origin, and those in, let's say, orange are all the destination. If you can play the video. Yeah, here we strolling around all the possible origins. And so this gives you an understanding of the complexity of the task and the flows that occurs in an urban environment. You can stop, thank you. And from the feature side, so for each cell, we sample the orthophoto, and we use 2 foundation model, general dyno, and more specialized SATLAS. That one is based on VIT architecture, and the other on a SWIN. Both of them produce a feature vector of 1024 elements. And the embedding then becomes the node features of a GNN, while the edge features are simply the pairwise distance between each cell. The node features and the edge features are fed into a GAT, that is a GNN with the attention layers. And some details on the training strategy. So first of all, we use inductive learning to test the generalization capabilities of this approach, still within the country boundaries. But how I will show, we found out that the model has very strong generalization capabilities and is able to have strong performances on cities that were outside of training. And this is really important because let's say, retrieving empirical mobility data is really expensive. And sometimes they're not even available. For what regards the sampling of the training data, we use an edge sampler, and we balanced positive and negative edges to, let's say, mitigate an existing, let's say, natural data imbalance related to the fact that the baseline, as I was saying, is given by the Cartesian product of all the cells that you have in the data set. And the task is simply, at this stage, a binary edge classification. So we are predicting the existence or not of the flow. And the loss is a binary cross entropy, so as in every simple binary classification task. We weighted the loss using the distance between cells. The batch size was 1024, and training time 2 hours with a standard GPU, so it's kind of, let's say, it's a task not bounded by computing resources. And these are the performances we obtained. So on averaging on the test cities, we got an F1 score macro of almost 0.85 and a micro of 0.73 using the Dyno V2 embeddings that in this case were performing slightly better than the Atlas embeddings. So what we learned from this first experiment that we can use simply remote sensing images or overhead imagery to perform this task. That it enables a lot of scalability from our perspective. The performances are really good, and there's a transferability across cities that also is really important. This is a map that shows for each cell the individual F1 score measured against the actual destination of the flows. And as you can see, we have stronger performances where there's more activity. This is basically the city center, while in areas where there's zero or less activity, the performance of the model are worse. So this is due to the imbalance. What we are planning to do next is the flow estimation. So scaling from just saying, okay, people are moving from that area to another, to saying how many people are moving from an area to another. To develop the model, train the model for the whole nation, and try to use a discretization of the space that is, let's say, less coarse of 1 kilometer, so scaled down to the zoom 9 of H3 grid. For this, we have first result that is really promising. So this is an anticipation of what happens when you try to put the model, the prediction of the model on a road graph on the road network. And you do this basically stepping from the origin destination matrix to the road graph using the Dijkstra algorithm, so the shortest path. So we try for the demand generated from each origin to destination, then we compute the shortest path to go between those two cells, and we assign the traffic on the road network. And the performances you can see, I mean, here on the single element of the road network, which are the metric, which is, sorry, this is a mean average percentage error. So again, it's really good on the where there's more activity, that is represented by the thickness of the graph of the road network. But here you can see the scatter plot of the real flows per segment against the predicted. That is really good. We have an error squared of 0.9. So again, this is really, really promising and let's say enabling a lot of new opportunities for better model for us, in particular that we work a lot with mobility. And that's all. Thank you.
Thank you. Very interesting use case. We have time for a couple of questions. Already there.
Cool, yeah, very interesting problem. It seems very cool. I have one comment and then some questions. One comment is like, if you are using the normal Dino V2 weights, consider using the aerial weights. That might help you a little bit. But the other question was basically, are you just extracting the embeddings and then also training your, are you training like the whole pipeline, or are you extracting the embeddings and then just training your graph?
No, the foundation model is just the simple Dino. We're going to use the Dino RS we saw from your presentation. Honestly, we missed it. We saw it, the repo on GitHub is quite recent. But yeah, the foundation model is not fine-tuned, but we train from scratch the GNN that has to predict the flows starting from the features.
And have you considered just using a big transformer instead of a GNN? Because you know, there's a lot of people that make the argument that realistically, a transformer is actually just a GNN with like a fully connected network because of the attention, like the.
Yeah, we read some paper on this extreme point where you can see a transformer as a GNN. Maybe we're gonna do this test. Also, I invite you, if you have very technical question, to speak with Ludovico and Gianluca that did most of the technical work. So kudos to them. But yeah, it was for us, since it was R&D, an excuse to also try the GATT and the GNN. This is something really interesting. But yeah, we didn't yet test them against a transformer, a simple transformer. But yeah, I think that for how we need to define the problem with and create the graph at the beginning, it will be harder to translate it on the transformer, let's say, side. But yeah, we'll take this in consideration.
Any questions online? If there's no further question, thank you very much.
Thank you, everybody, and good aperitivo.
Well, we will then close the session. It's very impressive. We still have full house, more or less, at the end of the day. Yeah. Thank you.